I'll do it tonight then. Good morning. Good morning. Good beautiful morning. Good beautiful morning, everyone. Good morning. Good morning. Good morning. You know about the Nancy Pelosi good morning? No, I'll show you guys real quick. Good morning. Good beautiful morning. Good beautiful morning. Beautiful morning. What is it? There you go. Where's the sunshine? Oh, right here. Wait. Let the viewers see what I'm talking about.
Good morning.
Good morning.
Sunday morning. Good morning.
Good morning.
Sunday morning.
Sunday morning. It's Monday morning. Good morning. Good morning. Is this all? I don't know if this works. Roll boomer. Good morning. Sunday morning.
Voting the day that we lost Ruth Bader Ginsburg.
But to be clear, you're not taking any arrows out of your quiver. You're not ruling anything out.
Good morning.
Good morning.
Sunday morning.
This is funny. Like, these are the people who run our country, and like, good morning. Good morning. Beautiful Sunday morning. That's cool. She's cool though. Isn't she cool? She's pretty cool. All right, get back on track. Get back on track, son. You're behind. All right, this is here. What else we got? Good morning. Beautiful Sunday morning. Good morning. Good morning. Beautiful Sunday morning. I know it's Monday, but good morning. All right, I'll be back. I'll be back, and we'll continue. We'll do a 10-hour today. Choo choo woo woo. All right, guys, we're back. We're back. Time to get started. All right, let's go.
Solely
Good morning,
an
John.
increase in heart disease because there was no increase in heart disease. But that's a little bit of a logical leap, okay? Because we don't really have this idea that those observers were upset about the increase in heart disease or the increase in death rates. I'm sorry. It's kind of a tongue twister, but so I don't like C as much as A. So I'll say maybe not to C. And D says the increase in heart disease after World War II was somehow related to the decline in communicable diseases.
Okay.
Again, these people did not think that there was an increase in heart disease. And honestly, that's a good reason to rule out C as well. They didn't think that there was an increase in heart disease. So we can rule out C and D because of that. Correct answer would be A. Number 2 says the author suggests that concluding that diet is responsible for heart disease would be okay. So this is a main idea question. Let's go back to our main idea. Diet should be tailored to the individual by scientific professionals, not controlled by unsupported and
No, what happened? John's lagging. Ooh. Ooh. That was a pop. That's pretty good, though. That's some good oranges right there. Good morning. Beautiful Monday morning. It's a beautiful Monday morning. Good morning, good morning. The sun is out this beautiful morning. It's such a lovely day. Da-da-da-da-da-da-da. And it's such a lovely day.
possibly
Yes.
unsafe government regulations. The author suggests that concluding that diet, solely diet, is responsible for heart disease would be A, mistaking cause for effect. The author would think that say that heart disease would be responsible for your bad diet. That's what A is saying. That doesn't make sense. So maybe not A. B says mistaking correlation for causation. I think this one's actually kind of tempting because the science brain in me is like, oh yeah, anytime I see that, I'm gonna click it. But we didn't talk about correlation here. We didn't talk about heart disease being correlated to anything. We didn't talk about any kind of correlation. And so I'll say maybe to B, but we didn't really talk about it. And a lot of times silence on the MCAT is pretty loud. If they're not going to explicitly say it, a lot of times you don't click it. So I'll say maybe to B, but I think that I like B because the scientist in me is attracted to it. So I'll say maybe to B, but maybe not. C says failing to consider a common cause. Our author made like a big argument that like the diet should be tailored. I mean, the main idea is saying that the diet should be tailored to the individual. Our purpose for tailoring it is because there's like a billion different causes or a bunch of different contributors. He said diet's one of them, genetics, social factors, exercise. Our author actually talked about that. So I don't think that the common cause is a good idea. So say maybe not to C. And then D says failing to consider additional causes. Okay, this is what I like, right? Because our main idea says we're going to tailor the diet. Why are we tailoring the diet? Because there's a bunch of different factors to take into account. Our author is going to say that if we're saying that just diet is responsible for heart disease, that X equals Y, we're failing to consider the other variables. So I'll say I like D a little bit better than B. B was just the scientist in me being like, I love that. Number next says Edward Aaron's criticism. I think this is number 3. Yeah, Edwards, there's old Edward, is criticism as is presented in the passage essentially points to what? We've already kind of established that Edwards was used as a tool to support the main idea. So I can really rephrase this question as which of these does the author view dietary guidelines? But if you forgot who Edward was, don't just like try to answer it blindly. Like you should go back and find who Edward is and what he said. It's right there. Don't reread the whole passage though. That's where you get into trouble with your timing. Does our author think that diet is complex? Yeah. So I like answer choice 1.
Right.
Does our author think that dietary guidelines are flexible? I don't know about flexible. I think that once you get one specific diet for one specific individual, it's pretty rigid.
Yeah.
So I don't really like that. I don't
Okay.
like flexible that much. Does our author think that dietary guidelines involve diversity? Yeah,
Yes.
that's the thing. It's got to be individually tailored. Our main idea says it has to be individually tailored. That represents diversity. And it should be individually tailored by a scientific professional. Why? Because it's complex. Okay, do you see how I'm using the main idea to answer these questions by asking questions of my main idea?
Yep.
That's the way to do this.
Okay.
So I like 1 and 2. Or I'm sorry, I like 1 and 3. The only one that says 1 and 3 is answer choice D. You can get into trouble. I know what a lot of you do. I know I've done it. But you can get into trouble by saying like, oh, I like answer choice 1. Let me go rule out all the ones that don't have answer choice 1. And you rule out C. And then you come back and you're like, I don't know about answer choice 2. I kind of like it. And then you go down, you rule all the one. You can get in trouble by doing that. The best way to do this is read through all 3 or 4 Roman numerals, pick the ones that you think answer the question appropriately, and then go to find the answer choice that agrees with that. Okay, number 4 says the author mentions easily digestible carbs in paragraph 5, most likely in order to what? Okay, so again, it told me what paragraph to go to, so I'm gonna go there. 1, 2, 3, 4, 5. Several studies have concluded that easily digestible carbs, in particular, such as burn fat and also increase inflammation that can. But then he kind of went on to be like, oh, but we also can't really support that. Sucks. So what's the point of mentioning another dietary guideline? What does my main idea say?
Diet should be tailored to individuals by scientific professionals, and possibly unsafe government guidelines. Yeah. Where is my super suit? Where is my super suit? No, seriously, where did I put my glasses on? I'll be right back, guys. Oh, hold on, never mind. We found it. We found it. We found my glasses.
They're not great. They should be tailored by the actual doctors and stuff. So why should they be tailored? Because they are unsupported and possibly unsafe. So, okay. Answer choice A says to imply that the 1977 guidelines may actually have harmed public health. Maybe, right? They were unsupported, they're unsafe, they're possibly harmful. So yeah, I mean, I think the author would probably agree with that. Let's say maybe to A. B says to suggest that nutritional thinking changes over time.
That's the one I put.
That's kind of tempting. I've got it narrowed down between A and B right now because B doesn't sound bad. I just don't know if that was the purpose of talking about easily digestible carbs. I would actually say that our author is more of a subscriber to the idea that.
What would you say, John? John. Bing, boom, bing, boom. Bing, bing, boom. Whoa, whoa, whoa. I'm lagging again. I'm lagging or just my computer's just slow?
Guidelines change over time, but that appropriate nutritional thinking should be established and not change.
Okay.
Like it should change per individual. It should be tailored, but I don't know that he or she thinks that it should change over time. I like A a little bit more than B for that reason. C says explain one cause of the current obesity crisis in the United States. That was not the purpose of this passage. The purpose of this passage was to talk about how dietary guidelines kind of suck and how they are made off of political decisions that lack scientific rigor and could harm us. So maybe not to C. Then D says criticize the makeup of the dominant diet in the United States. We didn't talk about like which diet was most popular, even though probably is a carb heavy diet with fast foods and stuff, but we didn't talk about that. So I don't really like D either. That was not the main idea of the passage. That wasn't the purpose of the passage.
Okay.
And so narrowing it down between A and B, I'm actually going to go see if I can see anything about these 1977 guidelines. So it looks like these 1977 guidelines were up here when we were talking about decreasing cholesterol and how we should raise carbohydrate intake. So if we're going to decrease cholesterol and raise carbohydrate intake in 1977, the author's saying, hey, look, this has even changed. Now they're saying that we need to eat, drew my arrow too far. We need to eat more carbs. Some science says we need to eat more carbs, or some science says that carbs are what are causing this inflammation and this heart disease. So in 1977, they said, hey, you just got to pound carbs, honey buns all day. And later they're like, oh no, that might kill you. And so the author is saying like, hey, these guidelines in 77 that said pound oatmeal cream pies and cereal, that might have hurt some people.
Mm.
So that's why we need to be a little bit more careful, listen to the science and stuff like that, because you can hurt people. So I like A better than B for that reason. He's not saying that, hey, nutritional thinking changes over time. It's kind of okay. This is a little bit more of like a chill tone. Can't write very well. That's kind of a chill tone. This one is like eager. It's like you're hurting people. We should stop it. We should probably be a little bit more proactive about this.
Okay.
Number 5 says, which of the following, if assumed to be true, would provide the best evidence to support the author's conclusion about how government should promote health? Okay. So I just look at this as which of these fits closest in line with the main idea. A says making the presentation of nutritional information on food packaging mandatory was proposed by lobbyists. Okay, I mean, that's fine, but I don't think the author is necessarily saying that he wants more government mandates. So maybe not A. B says America's obesity rate was far lower when nutrition was largely parental responsibility. Well, yeah, that supports our argument, right? If that's true, that supports our argument because our author was saying like this diet should not be in the hands of the government. It should not be regulated. This needs to be individual. So I like B. C says most public health officials support some government involvement in nutritional policy. That would not support the author's conclusion because that would say that if some people are for it, then maybe they're all right or something like that. So that's kind of like tangential. And then D says government efforts to reduce smoking in the U.S. have been quite effective. Smoking and diet are different. I can see the common thread because they're both about health, but since we have an answer choice like B, that's pretty dang good. D is going to go in the trash because
No, because what, John, come back, buddy. I think I just
something like that. So
that tabs or something. I don't know. Let's actually go back because I want to see what he says about the first one.
A says making the presentation of nutritional information on food packaging mandatory was proposed by lobbyists. Okay, I mean, that's fine, but I don't think the author is necessarily saying that he wants more government mandates. So maybe not A.
Okay.
B says America's obesity rate was far lower when nutrition was largely parental responsibility. Well, yeah, that supports our argument, right? If that's true, that supports our argument because our author was saying like this diet should not be in the hands of the government. It should not be regulated. This needs to be like B. C officials support some government involvement in nutritional policy. That would not support the author's conclusion, because that would say that if some people are for it, then maybe they're all right or something like that. So that doesn't. That's kind of like tangential. And then D says government efforts to reduce smoking in the U.S. have been quite effective. Smoking and diet are different. I can see the common thread because they're both about health, but since we have an answer choice like B, that's pretty dang good. D is going to go in the trash because the MCAT can always say smoking and diet are different. Okay, so keep that in mind. If B wasn't there, if there were no good answer choices, you could argue for D, but B is there. You do have a good answer choice. So always go with what's safest. Always go with something that you know is true. Okay, number 6 says, which of the following criticisms of a proposed space shuttle flight, okay, where the heck are we going with this, is most likely that of the, quote, major scientific dissenters in paragraph 6 as the author presents their view. The CARS does this, I don't know why, but they do this to where they'll like throw in some like wacky off the wall scenario. I mean, we're talking about diet and you're like, hey, what if Elon Musk wants you to go to the moon? And it's just the weirdest thing ever.
Right.
But what they're trying to see is, can you figure out what the
how is this only 13,000 viewers? That's crazy.
Kind of like the sole push of these major scientific dissenters was, like why they had a problem with it, and apply it to a new scenario. That's all they're really trying to get at. So let's find them. Told us paragraph 6. Let's go to it and find it. I believe 1, 2, 3, 4, 5, 6. So it's this one. Major scientific dissent. I remember it was at the end. Oh, it was after this but statement. The major scientific dissenters are not especially... Okay, so their problem is not mainly with paternalism, even though they don't like it, but they dissent because they find the evidence inadequate and potentially harmful. Main idea, right? So this is one of those. Another one of those, actually seen like a couple today, but they're going to reference you to a paragraph, a specific location, but they want you to answer with the main idea.
Okay.
A says the composition of the shuttle crew violates equal rights legislation. Not really talking about equal rights anywhere in the passage, so I don't really like A.
Gotcha.
B says the shuttle flight is motivated mostly by political objectives. If you pick this answer, it's probably because you're highlighting. Okay, highlighting is...
Dang, he knew. John knew I was highlighting. I highlighted too much. How does he know? He's that good. He's just that good. He's just that good. Maybe we can get that good. We'll see. We'll see.
A tool that can really bite you in the butt on cars because it allows you to memorize specific things on the page without internalizing what they're supposed to mean to you.
I forgot to turn on the clock. Yeah, that's exactly what I did. Exactly. That's exactly it, John.
And really, the MCAT's mostly asking you to read between the lines. Okay. And so if you highlighted where they had a problem with it being paternalistic, you're probably going to pick B.
That's what I did. That's what I did.
So maybe not B. C says the shuttle assembly has serious design flaws. Would serious design flaws lack scientific excellence or rigor and be potentially harmful? Yeah. So I like C a whole lot. And then D says it's too expensive. And that's not related to the passage at all. So you have to find a common thread in these weird ones where they bring up an off-the-wall scenario.
Gotcha.
You have to find a common thread. And usually that common thread is somewhere within the main idea. And you'll notice like that's the very core of our main idea, is that we don't think diet should be unsupported or unsafe. And the government's making it so. Okay. And then the very last one says the author's arguments about government imply that he or she would be likely to oppose which of the following? Okay, so this is saying which of these does the author not like? Which of these does the author disagree with? A, legislation limiting the number of hours one can work per week. Okay, I don't really know what like the hours you can work per week has to do with anything, but I don't think our author would like the legislation limiting anything. B says a decrease in governmental subsidies to colleges and universities. Again, subsidies, we didn't really talk about them. We didn't even talk about education in general. But a decrease, our author seemed to be against paternalism, against government oversight or whatever. So maybe B is like something that our author would support. C says legislation loosening regulations on lobbyists. Okay, loosening. So this is less government again. And then D says a decrease in government oversight of school lunches. So this is less government again. So you see, this is it's kind of convoluted, and you're playing this weird scenario again. But when you boil this question down, you see that this is just saying like our author was saying government needs to stay out of crap. Which of these agrees with that? A says we need less government. I'm sorry. A says we need more government. B, C, and D say we need less government. So our author agrees with B, C, and D and disagrees with A. Rephrasing the question is very, very important. It can make some of these very difficult questions a little bit easier and a whole lot more manageable. A says which of these agrees with that? A says we need less government. I'm sorry. A says we need more government.
Yeah. Oh man. Wow.
B, C, and D say we need less government. So our author agrees with B, C, and D and disagrees with A.
Oh, that was so clean. Oh, that was so clean.
Rephrasing the question is very, very important. It can make some of these very difficult questions a little bit easier and a whole lot more manageable. That's all I've got for today. As always, make sure to give this button a like and subscribe to the channel so you can see us break down the rest of the exam. Thanks.
Thanks, John.
Today we're going to walk.
Hold on, John. I'm not there yet.
Passage number 1. Today we're going to walk.
Okay. Okay. All right, Lyle, let's go ahead and do. All right, let's go ahead and do the next. Am I allowed like paper or something on the exam? Just write stuff down. Just keep asking for a bunch of paper. Noteboard. How does the MCAT noteboard look like? How does it look like? What's an MCAT noteboard? Oh, looks like a grid. It looks like that. Is that how it actually looks like? MCAT prep and erasable noteboard booklet. Erasable noteboard booklet. For breaks. Gotcha. I should think about buying the exact same one now. Get even more prepared. Get even more, simulate the exam test even more. Simulate the exam even more. Whatever. Anyways, let's go ahead and all right, that's there. Let's go ahead and do the actual one now. So let's go ahead and actually probably, I guess I can just leave you guys on here. But let's go ahead and do the next one. Whoa, too much. Take them down. And go to user portal, go back. Oh, that was good. That was good though. I think he reviewed it really well. He read it real well, real thoroughly. All right, I've reconfigured it. I've reset it. Let's go ahead and start it up. Only I can wear any glasses or anything. And there's a CP, which we already went over, so don't look, because I don't want to have to memorize the questions. I want to have it be fresh for when I redo this again. I'll go through these later on. So, no, thank you. Cars, we just did, so let's go ahead and skip those questions. In the section. And I believe this one is gonna be BB. Yeah, this is BB now. Yep. I really want it to be colored. Maybe we can just do it. I don't know, just do regular one, I guess. All right, so I'm going to take BB Passage 1, Biological and Biochemical Foundations of Living Systems, Passage 1, and then we'll go ahead and review with him. We'll go ahead and review with him after I'm done, see what was what. All right, 134. 134, how many questions? 5 questions. And I think it's probably, maybe it's 8 minutes. So we'll do 126, I think. 126. 126, let's see where that gets us. Yeah. God. All right, let me think about this. Yeah. It's a coenzyme. That's a coenzyme, I think. It said it can be bound to multiple. That's such a good one. Let's see this one. So it turns GTP to GTP. Try to dies as a phosphatase. Remove the phosphate groups. The nucleus. Oh, wait. No, I don't think so. I think this one makes sense. I think maybe this. I think this one. Oh, okay. We'll see. All right, John, let's go over this one then. Hey, buddy. Let's see what I thought was correct. Actually, maybe let's see. Let me just kind of review my answers real quick. I think so. I mean, I won't be able. I think so. Let's just go with it. gotta keep going up. I gotta keep going to determine my score. Let's go. Yes, I want to have the exam scored. Ooh! I mean, not bad. Not bad. Not bad. Hey, that's not bad at all. No, let's go back. Let's go back. I got 3 out of the 4. Hey, that's pretty good. But I feel like it took a bit too long. Yeah, how long did it take? I think it definitely took too long. That's okay. And that's okay. As long as you understand it. Yeah, I think that's more for an amino acid, which is right. 3, I can't regret. But number 4, what was number 4? Endoplasmic reticulum. Oh, of course. No wonder. Okay. All right. Well, I got 3 out of 4. I missed the 4th one. I wasn't really thinking, but I definitely should be doing it a little bit faster. But 3 out of 4, it is what it is. All right, John, let's go over it. Tell me how I should think, John. Tell me how I should think.
Test 1, BB section, passage number 1. Let's jump right into it. I'm going to read through this passage. I'm going to go ahead and make a flow chart. If you don't know what I'm doing is when I'm mapping out these passages, make sure to go back and watch our old strategy videos. There's one called Interpreting the MCAT, or How to Interpret the MCAT. It's talking about this method that I use called the flow chart method. And so, again, of course, we're always looking for basic sciences, and we're also looking for relationships. So, just for the sake of...
You said the flowchart method? But I don't go over flowchart method until week 3. So, I don't know. Whatever.
Brevity, I'm going to highlight the basic sciences, and I will write or draw out the actual relationships. The flowchart on the BB section actually gives you a lot of extra points, just some freebies. And hopefully we'll jump into some of that here. So it begins, it says proper biomolecular trafficking, including protein packaging by the Golgi apparatus. Okay, that's a basic science. Like, that's what the Golgi apparatus does, is it packs up proteins that are destined for secretion, essentially, and it kind of labels them as such. It's like the post office. Is essential to the compartmentalized eukaryotic cell. Therapeutic agents that disrupt the function of the Golgi apparatus reduce cell viability and can serve as effective treatments for carcinoma. So here we have that if we have these therapeutics that actually decrease the function of the Golgi, so decrease Golgi, I'm just going to say GA for Golgi apparatus. If we decrease the function of the Golgi, that can lead to decreased cancer, which makes sense. Like, we kill a vital cell function, then we're going to end up killing the cell. Goes on to say ADP ribosylation factor, or ARF1, plays an essential role in vesicle formation, is responsible for the recruitment of cytosolic protein coat complexes and subsequent retrograde transport from the Golgi. Okay, that should sound like word soup to you. You're not supposed to know what ARF1 is. You're not supposed to know what COPs are. I mean, but not in this scenario. You're not supposed to know I don't even remember learning about retrograde transport. But because of the basic sciences within these terms, we can kind of figure out what they do. But we can definitely figure out the relationships. And so that's what I'm going to mainly focus on here is their relationships.
All right.
So it says that RF1 helps with vesicle formation. So RF1 forms vesicles, is responsible for the recruitment of cops. So RF1 also recruits cops, which it says subsequently leads to retrograde transport. So leads to this transport from the Golgi apparatus. This is retrograde. So that means we're kind of reversing course. Okay, so the question you ask yourself is, okay, well, if it's retrograde transport, then where do proteins come from before they're at the Golgi?
Right. That's what I
And
thought.
the answer to that would be the endoplasmic reticulum. So the general order would be the ER goes to the Golgi, which goes to secretion. But if we're going in a retrograde fashion, then going backwards here. Okay, that's all that really means. It's nothing that you had to super have memorized, but you can kind of figure that out. Okay, so that's a good little
Yeah, it's kind of stuck on
relationship there
retrograde.
right off the bat.
Well, that makes sense.
It says R4 is activated by GES. Okay, so we got another relationship here. So R4 is activated, so increased function.
Maybe so you guys don't think I'm like lying or something here. Like, I don't know if I can, but maybe not. I think he like copied it. I don't know. I don't want to show you guys, but I got one correct, second question correct, third question correct, fourth question I got wrong because of what John talked about the retrograde. I thought it was we're transporting stuff like back to the Golgi, not to the Golgi, but backward retrograde. So I kind of a little bit thought that, but I didn't really lock it in like that. So yeah, it's just such a clean explanation. Like we're just going backwards. Okay. Yeah. Well, now I know. Anyways, I got 3 out of the 4. So you guys know that I know. So you guys know that I'm not lying. The first one. Oh, actually, maybe I can just show it. Can I show it? I don't know if I can show it. I think maybe I can show it. Maybe just not include like I don't know so much of the other stuff. I guess. I mean, I think since he has it, it's probably not that bad, right? Anyways, you can see I got C correct, which is the first one. I got the second question correct, and I got the third question correct. But the fourth question messed me up because I forgot about the concept of the retrograde. But it made sense. So, anyways, we'll see John's explanation and make sure we're doing good for next time. Let's go back to share. So not bad. I'm 3 out of 4. I'm happy with that for now. Not bad.
By GES, which replaced guanosine diphosphate or GDP with GTP.
I think I'm gonna have a little notepad something during the test. So I think just at least being able to just write stuff down like how he's doing, I think that's something I should be doing as well.
So GES lead to increased GTP or increased phosphorylation, let's say. Kind of makes me think like right off the bat, like I guess you're a kinase maybe if you're increasing phosphorylation. But we'll see. I'll have to think that through a little bit more. It says upon GTP exchange, RF1 undergoes a conformational change that releases the myristoylated N-terminus of the polypeptide chain from a structural group in the protein and initializes localization to the phosphobilipid layers. All I really care about that is that when we have this GTP shift right here, when we have this GTP exchange, then we are localizing these proteins to the phospholipid bilayer. So I'm going to say,
Oh, nice. You switched
I'm going to
it.
say GTP shift, or I'll say delta. So a change in GTP is going to lead to increased phospholipid, or I'll say PL for phospholipid
Oh,
localization. Now notice that these are not like super extensive notes. This isn't something that I could come back to, in 3 days and know what I was getting at. But because I have just read the passage 5 seconds earlier, I will remember it for the portion of getting the questions right. And that's my whole goal in the MCAT. I don't care what anybody says. You can't convince me that there's a goal within the MCAT other than getting questions right. That's all I care about. And this is a really efficient way to do it within the allotted time.
yeah, I agree.
What's associated with the bilayer, RF1, and this is increased phospholipid localization of RF1. You could put that if you want to make sure that you know what you're getting at. It says, once associated with the bilayer, RF1 further facilitates vesicle formation by the recruitment of heterotetrameric dimers of dimers. So that's a basic science. Codomer protein complex COP1 subunits are beta, delta, gamma, and I'm really not sure what this Greek figure is. Maybe epsilon. I don't know. So we recruit those. You can write that if you want. RF1 GTPase activating protein, or the GAP, catalyzes the conversion of RF1 bound GTP to GDP and inorganic phosphate, thereby converting the protein to the inactive form. Okay, that's pretty big right there. It says this GAP protein, which is the RF1 GTPase, converts RF1 bound to GTP. So I'm going to say GTP to GDP. So we can identify what type of protein that is, and inorganic phosphate, thereby converting the protein to the inactive form. So that leads to inactive RF1. So now I know that active RF1 is phosphorylated or attached to GTP. Inactive is attached to GDP. GAP activity is increased by RF1 binding to this weird complex. This is always important. Whenever they tell me that something is increased or upregulated, that's a super important relationship. And so I'm going to go ahead and write down for increased GAP activity is increased by, or related to an increase in the beta delta COP1. I know I didn't write the whole thing, but I'll know what I'm getting at. And then it goes on to say Bruffeldin A, or BFA, is a lactone component isolated from fungi, has been shown to inhibit RF1-driven vesicle formation. Okay, resulting in reversible disruption of the Golgi apparatus. Okay, so we could say that BFA kind of decreases RF1 activity, if you would like to. So we can say BFA leads to decrease RF1. Notice what I'm doing here is I'm just trying to get a list of like simple relationships, so that instead of having, if I get asked a question that's essentially what does BFA do and how's it working, I don't have to go through and like reread all this stuff. I can just go back and look at my notes, and it says BFA leads to a decrease in RF1, and then I can go back and be like, well, how does RF1 work again? And I go up here and I say, oh yeah, RF1 works by being attached to a GTP. So this paragraph again says BFA shown to inhibit RF1 activity, resulting in reversible disruption of the Golgi apparatus and tumor remission in vitro. So that's kind of pulling it full circle to when we were talking about the Golgi apparatus earlier. Because of its low bioavailability, BFA is not a suitable candidate for pharmaceutical deployment. However, it has led to the identification of AMF26 as a promising drug. So they're saying it kind of works, but we just don't have a lot of it. Maybe that's a question they asked, but probably not. AMF26 is predicted to bind to the protein-protein contact interface of ARF1, preventing GTP exchange by GEF and disrupting ARF1 membrane localization in the critical step of COP1 recruitment and vesicle formation. Okay, that's a ton of relationships in there, but you don't have to write them down because you've already got all of those. This paragraph should have made sense to you if you followed along with the relationships. In clinical settings, oral administration of AMF20
So what's the timing breakdown? How long do I have? How long do I have? I have 8 minutes. I got 8 minutes. Why did I say 10 minutes? It was 8 minutes. So I'm over by like 2 minutes. That's not that good. I mean that's really bad.
26 has led to remission, preventing GTP exchange by GEF and disrupting ARF1 membrane localization in the critical step of COP1 recruitment and vesicle formation. Okay, that's a ton of relationships in there, but you don't have to write them down because you've already got all of those. This paragraph should have made sense to you if you followed along with the relationships.
Yeah, both of them made sense to me. Yeah.
In clinical settings, oral administration of AMF26 has led to remission of breast cancer xenografts in mice model.
But what was in vitro again? Was that one outside? Outside? I think right. I think so, right? In vitro. Oh, that's inside. Conducted outside of a living organism. No, in vitro is outside, and then I think in vivo is inside. Yeah, okay.
So I am going to say AMF 26 leads to decreased cancer. Of course, that's a hard line that I would not be willing to draw anywhere else besides the MCAT, which kind of relies on generalities. But that's it for the passage. So you notice, first BB passage I'm breaking down with you, there's a ton of relationships, and that's going to be consistent. So now let me go and show you how those are applied to the questions. So looking at this first question, it says hydrolysis of the gamma phosphate of GTP bound to ARF1 results in what? So this is essentially just saying is if we have GTP, we hydrolyze it, meaning we use water to chop it off, we end up with GDP, right?
Plus PI.
What does that do to ARF1? Well, we found out earlier in our flow chart. Right here, we see that gap. It's this large relationship, but all it's saying is that we have a shift from GTP, or I'm sorry, it's right here. We have a shift from GTP to GDP, and that inactivates ARF1. So that's really easy. That's a free question right there. The correct answer is inactivation. So the flowchart can really score you some easy points as it did there. The second one says the ARF1 activating molecule GTP is most closely related to which family of biomolecules? So what type of biomolecule is GTP? Okay, GTP is guanosine triphosphate. They even lay it out for us in the passage, which is going to be a nitrogenous base, like a DNA base attached to 3 phosphates. And so looking at A, are nucleotides in GTP? Yeah, it's part of the guanosine. So maybe A. B, is there an amino acid in that? No. Nitrogenous bases nor phosphates are not examples of amino acids,
right,
lipids, or carbohydrates,
right,
but they are examples of nucleotides.
Right.
The third one says GAP belongs to what class of enzymes? So first we need to figure out what GAP ends up doing. So we go back to our handy dandy flowchart. Here we see that GAP takes a GTP and it cleaves it. It cleaves a phosphate off.
Mhm.
Okay, so what type of molecule is going to cut a phosphate off?
It's a phosphatase.
Okay, we see
lots of
transferase
hydrolases.
is answer choice A. Transferase involves the adding the sub or the molecule that you're cutting off onto an additional molecule. So we don't see that though because we have this free float
The what?
or the molecule that you're cutting off onto an additional molecule.
Wait, what'd you say?
Transferase is answer choice A. Transferase involves the adding the sub or the molecule that you're cutting off onto an additional molecule.
The molecule that you're cutting off onto an additional molecule. Sorry, John. I need to look at my notes for what you're trying to say. I know I still have it in here somewhere. It's in here somewhere. I know it. I know it. Well, I don't think I... Did I write it in pen? Maybe it's in this one, though. I don't think so, though. No? Would it be? Did I throw it away? No! No! I don't think so. I think it's somewhere here, I'm just not. I think I might just be doing it a little bit too fast. Slow down, boy. Yep, right here. Found it. Found the notes. Links that glues molecules together using ATP, ligase, DNA, ligase synthase, isomerase, rearrangement of atoms without adding or removing anything, phosphoglucose isomerase. Ligase breaks down bonds without water or redox. Generally forming renewable bonds or ring structures. Aldolase and decarboxylase. Hydrolase, we have breaking bonds of water. We have serine hydrolase or lipase. I think also phosphatase in there, right? Phosphatase is in there too. Isn't it also phosphatase in there? Oxidoreductase. Transfer electrons or protons between molecules. Dehydrogenase, oxidase, transfers functional groups between molecules. Kinase. Transfers. And then kinase adds phosphate groups to the membrane. Kinase adds phosphate groups to the molecule. Oh, adds phosphate groups to the molecule. Heterokinase. Hetokinase? Aminotransferase. Okay.
So we don't see that though because we have this free floating phosphate. So once we cut off this phosphate off of GTP, we have a free floating phosphate. So maybe not A. We look at B, which is phosphatase. The definition of a phosphatase is just something that's going to cleave off a phosphate. So maybe to B. I like B. C says kinase. Kinase usually involves the addition of a phosphate group, and generally you pull that from some type of organic molecule like a GTP or an ATP. So this one's tricky. However, you can rule out kinase because a kinase would cleave the GTP, but it would take this inorganic phosphate, it would actually add it onto some other random molecule. Okay. We're not seeing that. We just see the inorganic phosphate kind of freely floating out there into the ether, or just the cytosol. And so maybe not to see then. And then isomerase involves this idea of like moving around the molecule but maintaining the same chemical structure. And that's not what we see.
Right.
So the correct answer here would be phosphatase. That's a pretty easy, basic question if your flowchart is telling you exactly what's going on.
Okay.
Number 4 says proteins that are encapsulated in RF1 COP-derived vesicles are bound for the what? Okay, this is actually something I kind of pointed out. Let's see what happens in the RF1 COP vesicles. So if we scroll up, we see that these RF1 vesicles recruit COP. So the RF1 COP vesicles take proteins from the Golgi apparatus and transfer them to the endoplasmic reticulum. That is that retrograde transport that we were talking about. And so the correct answer here is obviously going to end up being endoplasmic reticulum. We start at the Golgi, we go to the ER because that's retrograde. A normal non-retrograde transport, just normal transport would be start at the ER, go to the Golgi, then you get secreted. But retrograde is kind of backwards. Retrograde. So you kind of had to use a little bit of intuition of like prefixes there to figure out what that's talking about.
Right. Yeah.
But it's fairly easy to piece together. And the very last one says, based on the mode of action described for BFA in the passage, the drug would be most effective against what? Okay, so now we had to see what BFA is and what it's acting on. So let's go find it. It says that BFA decreases ARF1. Okay. So I'm going to have to go back into the passage because that doesn't answer the question yet for me. So I'm going to go back up here to where we're talking about BFA. It says it's derived from fungi. It inhibits ARF1-driven vesicle formation and disrupts the Golgi. Okay, so if we're disrupting the Golgi apparatus, which of these has a Golgi apparatus? There's only one of them. Correct answer here would be eukarya. Viruses don't have a Golgi apparatus. Bacteria don't have membrane-bound vesicles, so they don't have a Golgi apparatus. And archaea don't have a Golgi apparatus either. So you can kind of see that BB, it hides behind these really dense and difficult to get through passages, these super sciencey passages. But if you can take the time, if you can get really good at this part of it, this flowchart part of it, BB is an easy 130 to 132 perfect score on the exam, as long as you know your high yield sciences and you can properly flowchart.
Wait, say again.
So BB is an E at this part of it, this flowchart part of it. BB is an easy 130 to 132 perfect score. You can take the time. If you can get really good at this part of it, this flowchart part of it, BB is an easy 130 to 132 perfect score on the exam, as long as you know your high yield sciences and you can properly flowchart. So I hope I can kind of convince you of that, but if not, then there's plenty of passages left. As always, thanks for watching the video. Make sure you like and subscribe, and I'll see you next time.
Yeah, I'm gonna try flow. Yeah, I did a little bit of flow charting just instinctively, but I'm gonna definitely do more flow charting. I think on all the sections, to be honest. This is crazy. Thank you so much. Maybe I'll comment. Thank you, John. Thank you. Yeah, let me see, what was the timing on it?
There's a lot of people that say that time is the gradient, and the question 70 question expected. Subtract that from 35 minutes left on the expected time, 1 hour and 27 minutes. But my total time remaining, and I should finish this pack. Give it your best. Is it? At least 2 out of the 4 sections in the allotted amount of time. During the exam, feeling rushed can cause a lot of unwanted stress, and this can lead to huge testing drops in your exam score. You end up creating unwanted anxiety and wasting more time by thinking, oh crap, I'm behind, like, how am I going to catch up? And this is the very type of self-destructive thought process that you probably had the first time you took your first practice exam, or maybe even your first real MCAT. The best way to avoid that is by making a time chart. This is going to be accomplished through a series of steps I'm going to get to a little bit later in the video. Check the timestamps in the description if you want to skip straight to those. But first, let's understand the timing of the exam itself. The exam is going to be split into 4 sections. 3 of those 4 sections are going to be science passages: the CP, the BB, and the psych section. On the science passage, you're going to have 59 total questions, 10 passages per section, and 95 minutes to complete that section. Most questions will have an associated passage, but some questions will not. We're going to call those standalone questions. For each science passage, it's safe to give yourself 8 minutes total to read the passage and answer every single question.
Oh, 8 minutes. Okay. I should probably put that on the card. 8 minutes.
Because most science passages are either 4 or 5 minutes, the breakdown looks like you giving about 3.5 minutes to read the passage and organize your thought.
Okay, so
'They're about 1 minute to answer every single question. The card section, you're going to have 53 questions, only 9 passages, but only 90 minutes to complete them. This is usually the section that gives students the most trouble with timing. Cars passages have either 5, 6, or 7 questions per passage. This gives you 3.5 minutes to read the passage, about 30 seconds to gather your timing. Cars passages have either 5, 6, or 7 questions per passage. This gives you 3.5 minutes to read the passage, about
30 seconds right the main idea. $30 to write the main idea. I was definitely way too late on this one, but next time on the next passages, I'll make sure to include the timing charts, the flow charts, and the main idea for the car section as well. I mean, now I know. Before I didn't know. So, that's what it is. You know? That's why you got to thank John. Thank you, John.
.30 seconds to gather your thoughts and write your main idea, and 1 minute to answer each question. If you don't know what I mean by main idea, check out our strategy videos above. So knowing that we're essentially giving ourselves 4 minutes to read the passage and organize thoughts, and 1 minute per question to answer, we're going to give ourselves 11 minutes to complete a passage that has 7 questions.
Yeah, 7, 11. Yeah, it's 11 minutes.
10 minutes to complete a passage that has 6 questions. And
Doesn't
9 minutes
matter.
to complete
This
a
is the
passage that has 5.
breakdown, so I don't really need to know the total score. I just need to know the exact breakdown so that I know.
Questions. To calculate how many questions are in a passage, subtract the question number that you will end on from the question number that you begin on, and then add 1. So if this passage spans questions 13 to 19, I'll say 19 minus 13 is equal to 6, and then I'll add 1, and that gives me 7 total questions for this passage. Adding 1 allows you to include the question that you're currently on as part of that passage. For some people, this is going to be overly complicated, and they can just look at it and see how many questions are in that passage. But for others, you'll need to use that simple little math. Do whatever works for you. The way that we're going to keep up with that is by using a timing chart. That's the focus of today's video. A timing chart is an actual paper record of when you started that passage and when you should expect to finish it. We're going to create it in 3 steps. The first is identify how much time you have left for the entire section. You can find this simply by looking in the top right corner of your screen and taking the MCAT. Go ahead and write that number down. The second step, figure out exactly how much time you should be spending on each passage following the rules that we laid out previously in the video. Subtract that from the amount of time you have left. That's how much time you should have remaining on the clock when you finish that passage. So for example, if I begin passage 1 of CP with 1 hour and 35 minutes left on the clock, this passage should take me 8 minutes. That means I should finish with 1 hour and 27 minutes left on the clock. So I'll go ahead and cross out 1 hour and 35 minutes, and write down my expected time, 1 hour and 27 minutes, before I even begin reading the passage. Because the cars is a little bit more complicated, we'll say I begin passage 3 of cars with 1 hour and 10 minutes left on the clock. And the passage has 7 questions total. That means I should subtract 11 minutes from my total time remaining, and I should finish this passage when the clock strikes 0:59. may be a little bit difficult at first. Adding more math to a test and parts with 1 hour and 10 minutes left on the clock. And the passage has 7 questions total. That means it should subtract 11 minutes from our total
So 7 plus the 3.5, that's 11 minutes. So
time remaining. And I should finish this passage when the clock strikes 0:59. This may be a little bit difficult at first. Adding more math to a test. There's really more of a and try to, in my desire, that you get every single question correct on the MCAT. Change your work. You can do while you're not studying to help with timing is reading real books. Most timing struggles come from instead of scrolling on social media before you go to bed, and we use with our students. And if you're interested, playlist to watch. We're going to
thank you, John. All right, guys. So we finished that up. That was pretty good. I liked it. It is what it is. Let's go ahead and reset our test real quick. Why not? I mean, I don't know. Yeah, we might as well. We're gonna have to, anyways, right? So user portal. We'll go to MCAT prep free sample test unscored, and then we'll go ahead and reset her. Reset the test. All right, test is reset. Reload. And go to user portal. And that's it. Cool. So now let's go ahead and do well, what I want to do. Where are we guys at? Where are we? Oh yeah. Let's go ahead and get rid of some of this stuff now. Cell theory. Cell theory. Oh yeah. Yeah, we'll leave that there. Well, let's go ahead and start adding in the videos to watch.
Although enzymes are extreme,
All right, buddy, I'm here.
irreversible
And then we'll just go ahead and watch them all when we come back. And then we'll do the Anki review.
inside out.
And then we'll go ahead and start week 2 finally. See if we can do 4 sections today, I guess. When we finish early, well, we finish early. That'll be nice. That'll be nice. Yeah, that'll be pretty nice.
Hi everyone, and welcome to Biology Professor. Today we're going to talk.
Hello.
Hi everyone, and welcome.
Hello.
Human beings are made.
So loud, huh? So loud. What?
So the differences between homo.
Let's just put it down a little bit. You guys were way too loud. I'll probably do like this video. It's gonna take a while, huh? I'm thinking it'll probably take like an hour or two. But let me see what our Anki is at right now. Man, why does our Anki keep growing? It keeps growing because I'm adding content. I'm adding content. And I'm adding content. I don't know how long that is gonna take. Maybe like an hour or two, maybe. But these videos should help us be better. Some of it's gonna be reviews and then whatever, but we'll do the next. We'll definitely do the next 4 lessons today. Like, definitely do it. You know, I'm not messing around with that. I'm not messing around with that. I got so many tabs now. Wow, my computer's being slow. I need to close out some of these tabs. But I don't want to. I'm a tab hoarder. Call me a tab hoarder. I'm a tab hoarder. What is this? No, I can get rid of that. Anyways, let's I guess we'll start from here, huh? Let's put this guy over here. Somewhere over here. That's the next one. Right? Isn't that the next one? Let's check it out. Cell memory and overview. It's not the next one. cell membrane overview. Right here. That's the next one. So let's watch a little bit of these, Medina Repair 2. And then I want to watch this one. Let's watch all these. Go ahead and watch these ones. Let's watch all these. I think I missed a couple here. Whatever. And then let's go ahead and watch all these. And that's it. So we're starting it from here. Yeah, we're starting it from here. And then Anki afterwards, I'll pop that. That's already out there. So, alright, for now, let's take a 10-minute. We're gonna make sure we get it all done today. We have to, guys. We have to. Don't worry, we will. We will. 10 minutes on the clock. Ooh. Ooh. Ooh.
We should get back.
Hey guys, I'm back. Sorry about that. Way longer break than I thought. I was talking to my family. Anyways, let's go ahead and watch videos. I know we're late. We're late. But I got myself some yogurt, so it's kind of worth it. Kind of worth it. Look, here's the yogurt. I don't know if you guys can see. Yogurt. Let's throw this away real quick. Go ahead and throw this away real quick. Come back, we'll hit the hour. La-di-da-di-da, la-da-di-doo, la-di-da-di-doo. Hey man. Oh, we gotta do Anki. We gotta do the 4 sections. Let's get it.
An important biological catalyst that speed up the many reactions. Although enzymes are extremely useful and important biological catalysts that speed up the many reactions that take place within living organisms, enzymes themselves must actually be regulated and their activity must be controlled. And one way in which we can regulate the activity of enzymes is by using special molecules or ions known as inhibitors or enzyme inhibitors. And the two processes of enzyme inhibition that can take place are reversible inhibition and irreversible inhibition. So we're going to discuss these two types of inhibition processes in this lecture. So let's begin by defining and examining reversible inhibition. Now, when our inhibitor molecule or ion binds to that enzyme via weak electric forces, via non-covalent forces, and when that inhibitor can easily and effortlessly dissociate from that enzyme following the reaction, this inhibition process is known as reversible inhibition. So basically, in reversible inhibition, our inhibitor binds to that enzyme via weak non-covalent forces, and at the same time, it can easily dissociate from that enzyme at any given time. Now, there are 3 different types of reversible inhibition processes. We have competitive inhibition, we have non-competitive, as well as uncompetitive. And actually, there's a 4th type known as mixed inhibition, but we're not going to focus on that one in this lecture. So let's begin by discussing each one of these processes, beginning with competitive inhibition. Now, in competitive inhibition, our inhibitor molecule or ion actually binds to the active site of that enzyme because the structure of inhibition, our inhibitor molecule or competitive inhibition. Now, in competitive inhibition, our inhibitor molecule or ion actually binds to the active site of that enzyme because the structure of our inhibitor actually resembles the structure of our substrate. Now, since the active site is occupied by that inhibitor, that means momentarily our enzyme will no longer be active, and that substrate will no longer be able to bind into the active side of the enzyme because that inhibitor will be found inside that active site. So this situation is described in this diagram. So we have the enzyme, we have the substrate shown in green, we have the inhibitor shown in purple, and we have this whole is our active site. So let's imagine we have a 1-to-1 ratio of substrate to inhibitor. And so that inhibitor is just as likely to get into that active site as our substrate. So for this particular case, because we're assuming the affinity of this enzyme to the inhibitor is the same as to our substrate. So we see that once the inhibitor binds to the active side, this substrate cannot get inside, and so the enzyme is rendered inactive. Now, the special thing about competitive inhibition is the following. For a given fixed concentration of inhibitor, if we begin to increase the concentration of that substrate, for example, we create a 4-to-1 ratio of green to purple molecules. Now what happens is these green substrate molecules are much more likely to actually bind into that active side than compared to our purple inhibitor molecule. And that means by increasing the concentration of substrate, our substrate can basically compete and outcompete that inhibitor molecule. And this is basically what defines competitive inhibition and what separates competitive inhibition from non-competitive as well as uncompetitive. So for any given inhibitor concentration, the competitive inhibition can be reversed by increasing the concentration of substrate. That is, the substrate will begin to
Blah. In competitive inhibition, the inhibitor binds non-covalently to the active side of the enzyme because it resembles the substrate. Since the active side is occupied by the inhibitor, the substrate momentarily cannot bind, and this increases the activity of the enzyme. For only given inhibitor, for any given inhibitor concentration, the competitive inhibition can be reversed by increasing the substrate concentration. That is, the substrate can compete with the inhibitor for the active site.
compete and eventually will outcompete that.
And that one makes it. Excuse me. Oh, how long? Excuse me. Is that what? And that's what makes it reversible, huh?
That inhibitor. And once that substrate binds to the active side, that will activate our enzyme. So this basically means that if we increase the concentration of substrate high enough, eventually all the active sites will be replaced by that substrate. And that means the overall maximum velocity, Vmax, or the maximum rate of activity of the enzyme, does not actually change when we're dealing with competitive inhibition. And because we have to increase the concentration of the substrate to reach that maximum velocity, the Km, the Michaelis constant, has to basically increase. And this means that our affinity for that substrate by that enzyme decreases. Now, let's move on to our second type of reversible inhibition, known as non-competitive inhibition. Now, in competitive inhibition, the inhibitor resembles our substrate, but in non-competitive, the inhibitor does not actually resemble our substrate, and that means it does not bind to the active side of the enzyme. Binds to a completely different location known as the allosteric site. Now, since the two sites, the allosteric site and the active site, are different, the inhibitor can bind to the enzyme regardless of whether the substrate is actually bound to our enzyme or not. So if we look at the following diagram, we have the enzyme shown by this brown region. We have this active site, we have the substrate shown in blue, and we have this inhibitor shown in our with our purple color. So this here is the allosteric side to which our inhibitor will bind, and this is the active side. So what this means here is the inhibitor can bind to the allosteric site regardless of whether this blue molecule, the substrate, is actually found inside that active site. So once the inhibitor binds to our enzyme, it will slightly deform our enzyme. It will change the enzyme three-dimensional structure, and that will also slightly change the structure of our active site. And even though the active site can still bind our substrate, the binding is no longer optimal and the enzyme activity will decrease. So once the inhibitor binds to our allosteric site, that conforms or changes our enzyme, change the shape of the enzyme, change the shape of our active site. Now, even though the substrate can still bind to that active site to form the enzyme substrate inhibitor complex, this is no longer an active enzyme because this shape is not perfect, because this substrate does not fit perfectly into our enzyme. So that means at any given time, because we're going to have the inhibitor bound to our enzyme, that means we'll have less active enzyme molecules and the Vmax will be reduced. However, the ratio basically stays the same. So that basically means that the Km, our Michaelis constant, remains constant, which means that the affinity of the enzyme to the substrate will not be decreased or increased as it was in this particular case. And finally, let's move on to uncompetitive inhibition. Now, the major difference between non-competitive and uncompetitive is in non-competitive, this inhibitor can bind to the allosteric site regardless of.
Wait. Okay.
Whether the enzyme is bound to the substrate or not. But in uncompetitive, the inhibitor can only bind to.
Wait. I'm lagging. Seriously, dude? Come on. I'm pretty sure it's my computer. Why is my computer being so slow?
Our site on that enzyme when the substrate actually binds to our active site. In fact, in uncompetitive inhibition, when the substrate shown in blue binds to the active site of the enzyme here, when that binding takes place, only then do we create that site for this inhibitor. So we can imagine this binds, then it creates that site for our inhibitor shown in purple that can then bind to that site to form this enzyme substrate inhibitor complex. So that's the major difference between non-competitive and uncompetitive. So In this inhibitor process, the inhibitor only binds to the enzyme once the substrate is actually bound to that enzyme. And once it binds, it basically deactivates that enzyme. So in this case, the binding of the substrate to the active site creates a new site to which the inhibitor can bind. And once it binds, do we create is bound to the substrate or not? The substrate shown in effect side is bound to the substance or increased as it be reduced. However, the ratio basically stays the same, so that the affinity of the enzyme to the substrate will not be decreased or increased as it was in this particular case. And finally, let's move on to uncompetitive inhibition.
Yes, sir.
Now, the major difference between non-competitive and uncompetitive is in non-competitive, this inhibitor can bind to the allosteric site regardless of whether the enzyme is bound to the substrate or not. But in uncompetitive, the inhibitor can only bind to our site on that enzyme when the substrate actually binds to our active site. In fact, in uncompetitive inhibition, when the substrate shown in blue binds to the active site of the enzyme here, when that binding takes place, only then do we create that site for this inhibitor. So we can imagine this binds, then it creates that site for our inhibitor shown in purple that can then bind to that site to form this enzyme substrate inhibitor complex. So that's the major difference between non-competitive and uncompetitive. So in this inhibitor process, the inhibitor only binds to the enzyme once the substrate is actually bound to that enzyme. And once it binds, it basically deactivates that enzyme. So in this case, the binding of the substrate to the active site creates a new site to which the inhibitor can bind. And once it binds, it deactivates our enzyme. And in this particular case, the Vmax, the maximum velocity, the maximum rate of activity will decrease because now we have less enzymes that are active, and that will also decrease our Michaelis constant. Now, let's move on. Oh, and one last thing I want to mention. Basically in our competitive inhibition, we saw that by increasing our concentration of the substrate, we can basically kick out our inhibitor from the active site.
Right.
Now, for this particular case, because the inhibitor does not actually bind to the active site, no matter how much we increase the substrate concentration by, that will basically not kick off our inhibitor. So that's the major difference between competitive inhibition and these two types of inhibition.
Gotcha.
Now, what exactly is irreversible inhibition? So remember, we have reversible and irreversible. Now, irreversible inhibition basically means that once the inhibitor binds to our enzyme, it will be extremely difficult to actually unbind that enzyme and inhibitor complex. So in this inhibition, once the inhibitor binds to the enzyme, it is very difficult to actually unbind it from that enzyme. And the binding can either be covalent or non-covalent. So all three types of these reversible inhibition processes are non-covalent, but the irreversible inhibition can be non-covalent as well as covalent. So whenever you hear covalent bonding, that usually means irreversible inhibition. So this diagram basically shows one form of irreversible inhibition. So basically we have this purple inhibitor binds to some location on the enzyme that blocks this substrate from binding onto the active site. And on top of that, this inhibitor, it will be very difficult to actually take that inhibitor off from our enzyme. And this is the major difference between reversible and irreversible. So reversible basically means once we bind our enzyme, or once we bind our inhibitor to the enzyme, we can easily dissociate it, and the bonding is always non-covalent. But in this case, it can be covalent or non-covalent, and once we bind it, we cannot dissociate it very easily. For reversible, we have three different cases. We have competitive, we have non-competitive, and uncompetitive. In competitive, basically the inhibitor resembles our substrate, and so it binds directly to the active side, and that means if we increase the concentration of our substrate while keeping the inhibitor concentration the same, we increase the ratio and we increase the probability of this substrate binding to that active side. So we can basically displace that inhibitor from that active side. But in these two cases, our inhibitor does not actually bind to the active side because it doesn't actually resemble the structure of our substrate. In non-competitive, we see that the inhibitor binds to an allosteric side regardless of whether or not the substrate is bound to that active side. But in this case, the inhibitor can only bind to that special side when the substrate binds at the active side, which creates that pocket, that side for our inhibitor.
Side. Okay. I don't know if we have to go really dive deep, but we might as well, right? Anyways, we have all these videos to watch, so we got, and I want to watch these DNA repairers again real quick. We got these. I want to hit these. Hit these. I don't know if this is the same thing as the other one. I don't think so. I don't know if I hit these or not. And then we'll keep going. And then after that, we'll do Anki. After Anki, we'll hit, if there's time, I hope there is, but we'll hit 1, 2, 3, 4. We'll hit these 4, and then that'll be the end of the day.
Inhibitors are molecules that bind onto active sites of enzymes and inhibit that enzyme's functionality. Irreversible inhibitors are molecules that bind onto active sites of enzymes and inhibit that enzyme's functionality, inhibit their activity. Now, the thing about these...
let me change my jacket. It's getting too hot. My brain can cook. They're cooking my brain. My brain with all the knowledge. Cooking my brain, Andrew. Cooking my brain, mister. Thing. Whatever. I think it's a bit too tight. All right, we'll get some. We'll get food after this.
Irreversible inhibitors is they can bind onto the active side either. Now, the thing about these irreversible inhibitors is they can bind onto the active side either by covalent or non-covalent means. But once they bind onto that active side, they will not let go. And that means they bind very, very tightly, very, very strongly. And even if we remove excess inhibitor from that mixture, that will not dissociate that inhibitor, that will not reform that active version of the enzyme. So all the different types of inhibitors, irreversible inhibitors that we have in nature and that we can synthesize in a lab can basically be categorized into three different groups, into three different categories. We have group-specific inhibitors, we have substrate analogs, also known as affinity labels, and we have suicide inhibitors, also known as mechanism-based inhibitors. Now, we can actually use these three different types of irreversible inhibitors to actually probe and study the residues found inside active sites of enzymes. And out of these three different types of groups, the most specific type of group is the suicide inhibitor, and the least specific type of group is the group-specific inhibitor.
Okay.
So let's begin by discussing the group-specific inhibitor. Well, the least specific type of group is the group-specific inhibitor. So let's begin by discussing the group-specific inhibitor. Well, the group-specific inhibitor is an example of an irreversible inhibitor that binds to and reacts with specific side chain groups of amino acids. For instance, on the board, we have two examples of group-specific inhibitors. We have iodoacetamide that reacts with cysteine side chains, and we also have diisopropyl phosphofluoridate, or simply DIPF, that reacts with serine amino acids. For instance, if we take an enzyme that contains an active site, and inside that active site we have a catalytic amino acid, namely the cysteine, well then this iodoacetamide will react with that catalytic amino acid, the cysteine, to form a covalent bond between this carbon here and this sulfur atom here. And because this is the sulfur atom, part of the side chain of the cysteine that is used to basically catalyze some specific type of reaction, because we form a covalent bond as shown in the following diagram, that essentially deactivates, it inhibits the activity of that particular enzyme. And so as a result of this covalent modification, we essentially deactivate that active site of the enzyme. And notice in this process, we essentially kick off the I dive, and we also break off that H atom. And so we form this molecule as shown here. The H has a positive charge, the iodide has a negative charge. Now, this is the other example. And in this particular case, we see that diisopropyl phosphofluoridate actually reacts with serine amino acids. For instance, we know that in the active site of acetylcholinesterase, we have these serine amino acids that catalyze the reactions. And so if we mix this active site, so an enzyme that contains an active site with a serine, then this diisopropyl phosphofluoridate will essentially form a covalent bond between this phosphor and this oxygen, and that will kick off the F, the fluoride, and also that H to form the following covalent modification. And so these are two examples of group-specific irreversible inhibitors. Now, let's move on to the second type of category known as substrate analogs, or more commonly, affinity labels. So the thing about these affinity labels is the structure of that particular irreversible inhibitor actually resembles the structure of the natural substrate that binds into the active site of that enzyme. So these irreversible inhibitors are molecules that resemble substrates. And this allows them to actually fit into the active site of that enzyme. And once inside, they essentially react in a covalent manner. They modify the residues found inside the active site in a covalent manner, and that inhibits that enzyme's activity. Now, what's one example of an affinity label? Well, when we'll discuss the process of glycolysis, we'll see that an intermediate molecule in glycolysis is known as dihydroxyacetone phosphate. And what happens in glycolysis is dihydroxyacetone phosphate is transformed into another isomer by an enzyme we call triose phosphate isomerase. Now, inside the active site of triose phosphate isomerase, we have this glutamate molecule. And this glutamate molecule, the amino acid glutamate, essentially is responsible for this catalyzation process from transforming dihydroxyacetone phosphate into another isomer. Now, if we add bromoacetyl phosphate, this molecule, into the mixture, notice how this is almost exactly the same in structure as this original natural substrate. The only difference is instead of this hydroxyl group, we have this bromide. And because of that, this will act as a substrate analog, an affinity label. And what happens is this carbon here reacts with this oxygen to form a covalent bond, a covalent modification.
All right.
And that kicks off that bromide. In
There
the
we go.
process, because
Kick it
we
off.
formed the covalent modification, that essentially inactivates the active site of that enzyme, the triose phosphate isomerase. And now this enzyme cannot convert this molecule, the dihydroxyacetone phosphate, into its isomeric form. And we'll talk much more about that in our discussion on glycolysis.
Okay.
Now, let's take a look at the final category, suicide inhibitors. So these are the most specific type of irreversible inhibitors. And what that means is we can build and we can use these suicide inhibitors to basically bind to specific active sites of specific enzymes. Now, suicide inhibitors are also known as mechanism-based inhibitors. And that's because these suicide inhibitors, they can actually bind onto the active site of that enzyme and begin the normal catalyzation process as if this was a normal substrate molecule. However, down the line, somewhere down that pathway of that reaction, what will happen is that suicide inhibitor will produce a reactive intermediate that will modify the active site in some covalent way. And once that modification takes place, that inhibits that enzyme irreversibly.
Done.
And so 2 examples that we commonly use in medicine of suicide inhibitors is penicillin and aspirin. So remember, in our discussion on irreversible inhibitors, we said that penicillin is essentially an antibiotic. And this penicillin molecule binds into the active site of a specific type of enzyme used by bacterial cells to build bacterial cell walls. And this enzyme is known as transpeptidase. So bacterial cells use transpeptidase to basically build cell walls. And what penicillin does is it acts as a suicide inhibitor. That is, it binds into the active site of that enzyme and it begins the catalyzation process. But somewhere down that line, it forms an intermediate that essentially blocks and inhibits the activity of that enzyme, the transpeptidase.
Wow.
Now, aspirin, which has the following structure, is a suicide inhibitor to an enzyme we call cyclooxygenase. And what cyclooxygenase normally does is it basically catalyzes the formation of a special type of signal molecule that is used in the inflammation process. And so when we actually ingest aspirin, aspirin acts as a suicide inhibitor and it binds into the active site of that cyclooxygenase. And so what that does is it disables the ability to produce that signal molecule. And so the inflammation process cannot take place properly. And so that relieves pain, it decreases pain, it removes headaches, and so forth. So another type of suicide inhibitor that we commonly use is AZT. And AZT is a molecule that acts as a suicide inhibitor, and it basically treats HIV. So these are the 3 different types of irreversible inhibitors. So we have group-specific inhibitors, which are basically these irreversible inhibitors that bind onto specific groups, specific residues, specific amino acids. We have substrate analogs, also known as affinity labels, that essentially resemble that substrate, and so they can fit into the active site of that substrate and modify that particular active site in some covalent way. And we also have suicide inhibitors that basically bind into that substrate, bind into the active site, and they begin the normal process as if they were the normal substrate molecule, but somewhere down that reaction pathway, they essentially create a reactive intermediate that modifies the catalytic residue found inside the active site in some covalent way.
Fascinating.
And that inhibits the activity of that enzyme.
Thank you so much, sir. Thank you so much, kind sir.
In our body, we have all these different types of processes which are catalyzed by enzymes. So in order to actually study the behavior of enzymes and how they catalyze reactions, we have to study the rates of
Wait. I want to make sure that it makes sense. DNA cloning should go with chromosomes. Alternative splicing. Heterotrophy should probably go along with what we're doing now. DNA repair. Yeah, heterotrophic DNA repair can kind of be maybe by itself along with DNA. Maybe somewhere here, no? And then DNA replication maybe can go here. And DNA proofreading and repair should probably go along with DNA proofreading and repair. And then melting DNA structure. We should put that with DNA, right? Yeah, let's go with DNA. Replacing translation. Maybe we should go after transcription. And then enzyme feedback. Let's just do that over here. Transcription and relation termination. Over there, Zuran, native gel, and Zuran. This can be all in its own category. All right, let's go.
Of these enzymes and inside our body, we have all these different types of processes which are catalyzed by enzymes. So in order to actually study the behavior of enzymes and how they catalyze reactions, we have to study the rates of these enzymes and the rates at which they catalyze the reactions. Now, one way in enzyme kinetics that we study the rates of reactions is by plotting the following curve. Now, on the curve, the y-axis is the reaction velocity V0 of that particular enzyme. And that's basically the rate at which the enzyme catalyzes its particular substrate. And the x-axis is the concentration of the substrate S that binds onto the active site of the enzyme. So what we essentially do is we carry out an experiment. So in the experiment, we have a beaker. In that beaker, we have the enzyme that we want to study. Now, initially, in the beaker, we don't have any concentration of substrate, and so the concentration is 0. And because no substrate is present in that beaker, no substrate will be bound onto the active site of the enzyme. And so the velocity, the rate of that enzyme will be 0. And so in trial 1, point number 1 is 0. Mm-hmm. Now, in trial 2, we then add a certain amount of concentration of S. Let's say this many S molecules, and then we measure that corresponding Y value, that velocity of that enzyme. And so let's suppose we get the following value, and so this is data point number 2. And now we add even more S concentration. And let's say we add this quantity that corresponds to this data point here. And so we continue adding these data points, and eventually every single time we do this for any enzyme, this is the curve that we're going to obtain. So notice what the blue curve tells us. Initially, at the beginning, when we have a relatively little amount of S in that mixture, this blue curve will resemble a straight line. So from about here to about here, this blue curve looks like a straight line. And what that basically means initially, when we add a small amount of concentration of S into our mixture, the rate, the velocity of that enzyme, the rate at which the enzyme catalyzes the reaction will be directly proportional. So we'll have a straight line with respect to that S, the concentration of substrate. But as we continue increasing the concentration of S, we see that the slope begins to decrease and the curve begins to level off. And eventually it approaches asymptotically the maximum velocity of that enzyme given by the red curve. Asymptotically means the blue curve never actually crosses that red line. So that horizontal red line basically describes the maximum rate of activity of that enzyme at which the enzyme can actually operate on that substrate and transform it into some type of product. This is what the blue curve actually describes. So to see this in equation form, let's take a look at the following equation. This equation basically describes what is taking place inside that beaker once we add the substrate. So initially, we have the enzyme by itself, and then we add the substrate, and the substrate is also by itself. But then what begins to happen is the substrate begins to bind onto that enzyme's active site, and we form an intermediate molecule known as the enzyme substrate complex. Now, going this way, the rate constant is K1. But once we form some of this complex, it begins to dissociate back into these two reactants, and the rate constant of that reverse reaction is K minus 1. At the same time, some of that complex, so we now have the substrate inside the active site, and the enzyme will begin to transform that substrate into the product. And once we form the product, it will dissociate from the active side to basically form these final molecules, the product and the enzyme in its individual form. Now, going this way, the rate constant is K2, and going in reverse, the rate constant is K minus 2. So this is the equation that basically describes what is taking place inside the beaker once we reach equilibrium, once we establish equilibrium. Now, what we essentially want to do in this lecture is we want to derive the mathematical equation, the mathematical expression that basically describes this blue curve. So can we derive such an equation? And the answer is yes. But before we actually begin our derivation, we want to simplify this equation. So instead of using the equation that describes equilibrium, we're going to assume that we're essentially at the beginning of that equation. So right at the start, when the time is approximately equal to 0. And at this point in time, the velocity of that enzyme is equal to V naught. Now, another important point about the beginning of the reaction is right at the beginning of the reaction, we have not yet formed a large amount of product. So right at the beginning, what happens is we have that enzyme that binds onto the substrate, and this takes place relatively quickly. And so equilibrium is established here between these and this complex quickly because this takes place very quickly. But the enzyme basically converts product relatively slowly. And so at least initially at the beginning, we don't actually form a lot of the product. Okay. So at a time of t approximately equal to 0, what that means is because we don't have a lot of product formed, this reaction will take place at a very, very low rate. And so by approximating that, we can essentially remove this entire equation and remove the K minus 2 term. And that's because this reaction takes place at a negligible rate. So once again, to simplify this equation here, we can instead study the reaction at the beginning, that is when the time is approximately equal to 0, right at the beginning of that reaction. At that point in time, the rate V is equal to V naught. So at this moment in time, very little product P has actually formed. And so the reverse reaction of the formation of the product, this reaction here becomes negligible, and we can basically remove that from our equation. And this will simplify our equation, and that will allow us to actually derive the equation that we're looking for. So this is the equation that we want to use. Now, what exactly is our starting point? Well, the starting point is right here. So we essentially begin by studying how that enzyme is functioning. And to study how the enzyme functions, we have to actually look at the enzyme as it is bound to that substrate. So in this particular case, so this is our starting point. And that's exactly where we get equation number 1. So equation number 1 basically gives us the rate law of this reaction here, as the enzyme actually has the substrate at the active side and it transforms it into the product. And so the rate law of this reaction is given by equation number 1. So the rate of this which is the V naught. Remember, the y-axis here describes the enzyme actually transforms the substrate that is bound to the active side. And so this V naught is the same V naught that we have along the y-axis here. So V naught, the rate at which the substrate is transformed in the active side, is equal to the product of the rate constant K2 of this reaction multiplied by the concentration of this molecule, the complex, this intermediate molecule. By the way, these are reactants, these are products, and this is an intermediate molecule that exists between the reactants and the product. Now, the problem with this equation is, remember, we ultimately want to basically derive a mathematical equation that describes this curve. And so what that means is, whatever this equation is, we have to be able to describe V naught in terms of the concentration S of the substrate. And this equation has ES. And what that means is we can actually use this equation, and we have to somehow replace the ES concentration with the S. And that's exactly what we're going to do in all these steps, as we'll see in just a moment. So in the next step, we basically want to ask ourselves, once we form this enzyme substrate complex, well, first of all, how do we form this enzyme substrate complex in the first place? Well, to form this, we have to go in this direction. And what's the rate law for the formation of this enzyme substrate complex? Well, that is given by equation 2. So the rate of formation of this enzyme substrate complex is equal to the product of the rate constant K1 and the concentrations of these two reactants. So E and S. Now, once we form the ES can basically go in two different ways. It can either go on and form this product, which is basically this equation number 1 that we described here, or it can go back and reform these two reactants. And equation 3 gives us the dissociation of that substrate from that enzyme. So the rate of dissociation of the enzyme substrate complex is equal to the product of the reverse reaction K-1 multiplied by this quantity here. Now, our ES complex doesn't only dissociate going this way, there's also a probability that it will dissociate going this way. And so when it dissociates going this way, we have K2 multiplied by the concentration of ES. So this basically describes the entire rate of dissociation of the enzyme substrate complex. So it can dissociate not only going this way, but also going this way. And that's why we have these two summations. So we sum this with this, and that gives us the rate at which our enzyme substrate complex actually breaks down. So before we actually continue, now we have to make an important assumption. And the assumption that we make is that our reaction is at a steady state condition. And what a steady state condition actually means, the intermediate that is involved in our reaction, the concentration of the intermediate is not changing. And the only intermediate we have in our reaction is the enzyme substrate intermediate. So what that means is the concentration of the enzyme substrate complex is not changing. And what that implies is the only way that this concentration is not changing is if this reaction going this way, if the formation of the enzyme substrate complex is equal to the dissociation of that enzyme substrate complex. So assuming the steady state condition, the concentration of the enzyme substrate complex will remain constant. And this means that the rate of formation of the enzyme substrate complex is the same of the rate as the rate of dissociation. So equation number 2 is equal to equation number 3 because we make this assumption of a steady state condition. So once again, a steady state condition means this concentration remains unchanged. And the only way that's true is if this K1 reaction is equal to these two reactions here. So the breaking is equal to the forming. And so that's exactly what we do in this step. We essentially equate this equation to this equation here. So we have K1 multiplied by these two concentrations is equal to K-1 multiplied by ES plus K2 multiplied by ES. Notice on the right side, we have these two same terms, and we can bring that out of our equation to get the following result. And now we can basically bring all the concentrations to the left side and all the K values, the rate constants, to the right side, and we get this equation. So the product of the concentration of the enzyme and the substrate divided by the complex concentration is equal to K-1 plus K2 divided by K1. And instead of using these three rate constants, we basically said this ratio equal to a new ratio defined by uppercase K with the M subscript. And this is known as the Michaelis constant. And the Michaelis constant is actually a very important constant, as we'll see in the next lecture. And the units of Michaelis constant are concentration. So we'll talk much more about this in the next lecture. And let's designate this as equation number 4. Now, if we take this new equation, this is equal to this, and rearrange it and solve it for the concentration of the enzyme substrate complex, we get equation 5. So we essentially bring this to this side, and we bring this to our denominator here, and we get equation 5. So the concentration ES is equal to E multiplied by S divided by Km. Now, for a moment, let's go back to that assumption that we made at the beginning. We said that we're looking at the reaction in its initial stages when the time is approximately equal to 0. Now, initially, when the time is approximately equal to 0, we have a lot of the substrate that hasn't actually bound onto the active site of the enzyme. And this means equation 6. So the total substrate found inside our beaker is equal to the substrate that is not bound to the active site of the enzyme plus the substrate that is bound onto the active site of the enzyme.
All right, let's pause it. I need to use the restroom. Sorry. I think I just something I ate yesterday. I don't know.
Enzyme. So summing these two values gives us the total amount of S found inside our beaker. But because initially, when we add a substrate, this quantity is so much smaller than this quantity because very little of that substrate is actually bound onto the substrate. If this is very small compared to this, then this by itself is approximately equal to this. For example, if this is, let's say, 1 million, and this is, let's say, 999,999, then this is very small, and this is approximately equal to this. And so that's where we get this result. And so what that means is, in equation 5, we can leave S as it is. What's up with this marker? 1 moment.
Lord.
Okay. So based on 6, what that means is we can leave this S as it is, because initially at the beginning, the total concentration of S as total is equal to the concentration of S that is not bound to the enzyme, because this quantity is very, very small. Now, let's move on to equation 7. So by the same analogy, we see that the total enzyme inside our mixture is equal to the enzyme that is not bound to the substrate plus the enzyme that is bound to the substrate. Now, the same thing, essentially, what we assumed just a moment ago, we cannot assume for the enzyme case, and that's because the concentration of the enzyme is usually much, much smaller than the concentration of the substrate. For instance, we can have 1 million of the substrate molecules, but only 100 of the enzyme molecules. And so what that means is we can no longer make the assumption that this is much smaller than this. And so in this particular case, we actually have to leave the equation as it is. Now, we want to use equation 7 to basically replace this quantity in terms of the total amount of enzyme and the enzyme substrate concentration. And so what we want to do is we want to use equation 7 and solve for this quantity here. Remember, in this case, because of what we did in equation 6, this is simply this here. This does not change. But we want to change E and replace it with something that contains ES. And so we take equation 7, we rearrange equation 7 and solve for this. We get that the concentration of the enzyme that is not bound to anything is equal to the total enzyme concentration minus the enzyme concentration that is bound to our substrate. And now we take equation 5 and replace this quantity with this here. And so we get the following result. Now we take this equation, we multiply this out, and we solve for the enzyme substrate complex concentration, because now we have this term appearing on the left side and this term appearing on the right side. So we want to solve for this enzyme substrate concentration, and we get the following result. So the enzyme substrate concentration is equal to the total enzyme found inside the mixture multiplied by the substrate concentration divided by Km, this constant we define here, plus the concentration of the substrate. So now we take this equation. So remember, let's go back to this equation 1. So this equation here is the equation that describes the V naught that we actually want to solve for. So we want to have an equation in which the Y value is the V naught, but the X value is the substrate concentration. And that's precisely why we want to replace this quantity. So now in this equation, we can take this and replace the ES with the right side of this equation. And that's exactly what we get here. And we call this equation 8. So we take this, we plug that into here, and we get the following result. Now, the final thing that we want to ask ourselves is the following. So what exactly is the Vmax? So the Vmax is the maximum velocity of that enzyme. It's the maximum rate at which the enzyme can operate. And to obtain the maximum rate, all the active sites on all the enzymes have to be occupied with the substrate. And what that means is the Vmax, so this Y value here is equal to, so if we use this equation, K2 multiplied by, well, what has to be the concentration of this for this to be the Vmax? Well, when the enzyme substrate complex, so when all the active sites are occupied, that means this quantity, the concentration of this, will equal to the total concentration of the enzyme. And that can be seen from this particular equation 7. So in this equation, we see that when this value is equal to 0, that means all the enzyme's active sites are filled with the substrate, because when this is equal to 0, this will equal to this. And so what that means is the Vmax is equal to K2 multiplied by the maximum value of the enzyme substrate complex concentration. And this maximum value can be a maximum of V total, of E total. So we replace this with this quantity here. And so we see that the maximum rate at which the velocity operates is equal to K2 multiplied by the concentration of enzyme where all the enzyme's active sites are filled with the substrate. And if we take this equation and solve for, E total, we basically get E total is equal to Vmax divided by K2. And now we take equation 8 and we replace E total with Vmax divided by K. If we plug this into here, the K2s will cancel and we're left with this equation here. So V naught, which is the Y value on the following curve, is equal to Vmax, which is basically this maximum Y coordinate multiplied by the concentration of the substrate S divided by Km plus the concentration of substrate S. And this is the equation that describes this blue curve. And notice in this equation, Vmax is a constant. It's simply this quantity that depends on the height of this red line. Km is also constant. It depends on these 3 rate constants of the 3 equations that we described a moment ago. And this S is simply the X value on the following coordinate plane. So the X is simply the concentration of the S. And this is exactly what we basically want to derive in the first place. This equation is known as the Michaelis-Menten equation. And the Michaelis-Menten equation is basically used in enzyme kinetics to study the rates at which enzymes actually operate and act on different types of biological reactions. Now, in the next lecture, we're actually going to study the meaning behind this equation, what this equation actually tells us about how enzymes behave and how enzymes act and operate on chemical reactions. In our previous discussion, we focused on the following graph, and we said that the graph describes how the rate of the enzyme in an enzyme catalyzed reaction changes when we increase the substrate concentration. So as we increase the substrate concentration, as we make the X value greater, we see that the Y value, the reaction velocity, V naught, the rate at which the enzyme...
Keep going with this guy all day. We gotta maybe stop it here.
Our cells are amazing molecular machines. Every day, they convert food into energy, such as ATP, that drives the millions of biochemical processes necessary for keeping us alive. The pathways used to convert substrates, such as glucose, into products are collectively referred to as metabolic pathways. The drivers of these metabolic pathways are enzymes. Enzymes are usually proteins that work to assist chemical reactions by building or breaking down molecules.
Yes, ma'am.
However, enzymes don't drive reactions at a constant rate. The rate of reaction can speed up, slow down, or stop completely according to the cell's needs. This process is analogous to an assembly line where raw materials are converted into products. The assembly line must be monitored to ensure that the supply of products does not exceed demand. If products are being created at a rate that is faster than they can be used, both resources and products are being wasted. The assembly line can produce at a slower rate or stop completely to prevent waste. In cells, this process is called feedback inhibition. Feedback inhibition is achieved through a process called allosteric regulation and plays an important role in many metabolic pathways. Enzymes have a unique area called the active site where substrates can bind. Enzymes that can be regulated have an additional area called the allosteric site. Downstream products can bind to this regulatory site, causing the enzyme to change shape and prevent it from binding with its substrates. This causes the entire pathway to halt, and new products are no longer formed. Conversely, when the amount of downstream product gets too low, the enzymes interact with their usual substrates and begin forming products again. Feedback inhibition plays a critical role in preventing cells from wasting resources and energy. Mutated enzymes that do not respond to allosteric regulation have been linked to disease states such as cancer. Many processes in our bodies rely on feedback inhibition to keep everything running smoothly and efficiently, maintaining homeostasis.
You have to maintain homeostasis.
Is between homotrophic effector molecules and heterotrophic effector molecules in biochemistry. Let's start this off by talking about the word origins of each of these. So homo means same. And in this case, these are substances that bind to the substrate site. They can sometimes be the substrate origins of each of these. So homo means same. And in this case, these are substances that bind to the substrate site. They can sometimes be the substrate or they can be other molecules as well. So for an example, oxygen binding in hemoglobin would be a homotrophic effect. The more oxygen you have, the more of those subunits that are going to the more of those subunits that are going to be in the R state. So if you have more in the R state, the curve itself tends to look more R-like. So we're affecting the shape of the curve by inducing those R state changes. Heterotrophic, as the word hetero means, other or allosteric, for example, would be one of those things. 2,3-BPG or CO2 binding in hemoglobin would be examples of heterotrophic. They don't compete with the substrate at the active site. But what they do is they affect the changes in the Km value. Is it shifted to the right or is it shifted to the left?
Oh. Okay. 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 In R states. R state. So if you have more in the R state, the curve itself tends to look more R-like. So we're affecting the shape of the curve by inducing those R state changes. Heterotrophic, as the word hetero means, other or allosteric, for example, would be one of those things. 2,3-BPG or CO2 binding in hemoglobin would be examples of heterotrophic. They don't compete with the substrate at the active site. But what they do is they affect the changes in the Km value. Is it shifted to the right or is it shifted to the left? Molecule chemistry. Let's word origins of these. So homo means same. That bind to. These are substances that, in this case, these are substances that means same. And this homo means same. And in this case, these are substances that bind to the substrate site. They can sometimes be the substrate or they can be other molecules as well. So for an example, oxygen binding in hemoglobin would be a homotrophic effect. The more oxygen you have, the more of those subunits that are going to be in the R state. So if you have more in the R state, the curve itself tends to look more R-like. So we're affecting the shape. Homotrophic effector molecules and heterotrophic effector molecules. What? Homo means same. And the molecules. Did I copy the same thing?
Talk about how the process of transcription is different in prokaryotes versus eukaryotes.
Okay.
Make sure that you understand what the process of transcription does, why it's important before you proceed with this video. Yeah. Specifically, transcription is the intermediate step that connects DNA to protein. So it's how genes are expressed in a cell. Genetic information is stored in DNA. An mRNA copy of the DNA is made. That's the transcript that's made in transcription, which we'll be talking about today. And then that gets translated into protein. I do have a video on the central dogma of molecular biology that goes into more detail on that process. If you want to watch that first and then come back to this video. Now let's get started talking about transcription and how it differs in prokaryotes versus eukaryotes. Remember, with prokaryotes, we're talking about mainly bacteria. And with eukaryotes, we're talking about plants, animals, fungi, algae, protozoans, things like that. So let's get started. Prokaryotic mRNA, that's what we are referring to when I talk about the transcript in most cases. So prokaryotic mRNA may be monocistronic or polycistronic, while eukaryotic mRNA is exclusively monocistronic. Gotcha. Now let's talk about what those words mean. Polycistronic is what we have happening right here. So polycistronic is where you've got one mRNA transcript, that's the black line here, and multiple polypeptides, multiple proteins, are made from that one transcript because there are multiple genes per transcript. So you can have multiple genes represented on a transcript and then multiple polypeptides coming from that. Polypeptides and proteins, we can use it.
All right, let's take a 10-minute. We got a lot on here to do. Like a lot. Do you dream? Do you dream? Do you deem this strategy effective? Oh, hey Jack. Hey Jack. Do you deem this studying strategy effective, or what do you recommend? Time to do math exam. Yeah, honestly, like I recommend following exactly what I'm doing if you have no clue on what to do. I have no clue on what to do, and there's also just so many different MCAT strategies. So I mean, well, I don't know. I wouldn't recommend doing exactly what I'm doing, but if you don't know, just you know, follow this. I mean, follow this guide, right? Follow this guide and follow the YouTube playlist, which is. Hold up.
Hey guys, welcome back to the channel. My name's Maggie.
Hey Maggie.
With all the
Hey Maggie. Which is here. So literally, just go to this channel here, and then follow it, and start from week 0, and then go up. And then Anki is going to tell you how to do Anki. He's going to do some sample tests here. John is, and then some other stuff here and strategies, whatever. Yeah, I'll probably do strategies. I'll do like a separate. I should probably watch the videos too. Like I would recommend watching all of these videos, every single one of them, which I plan to do, and then and then just following this, following this. 3 months. 3 months. I think there's an extra month here, but it's not. Like I think this is just like content review, and I think there's like another week to this one. Final month. I think final month, which is another month, the 4th month. It was just like all practice based. So that's pretty good. But I think the strategy works out, and then even if you go to week 0, I think there's 2 different strategies, whether you're just using the videos or whether you're using the books. But I don't know. I mean, I kind of like being able to just go back and forward, speed up time. With the book you can too, I guess. It's just, but I don't know if you can. Well, you just read it, but yeah, everyone has their own thing. But anyways, this works. I think this works, and it's simple. It's really simple. Like it's very simple. Like with all these extra videos that I'm watching here, they're only to fill in any content gaps that I have, and also it's because if we go to oh, I don't know if I can. Where is it? If we go to my Anki, like these were on some of the newer cards, and so I just want to make sure I'm not missing anything at all. Make sure I'm reviewing everything I can do. So yeah, I mean that's what it is. That's what it is. That's what it is, Jack. Good luck on your math exam. Good luck on your math exam. Anki every day. Anki every day. Where are my stats? Where are my stats? Oh, I kind of fell down now. I kind of fell a little bit down. That's okay. We'll get there though, and I think I missed. I don't know. Yeah. All right. Whatever. But that's what we're doing. That's the strategy. Strategies have no strategy. Just follow someone who's already done it. I'm not the first person to take the MCAT. Alrighty. Good luck, buddy. Good luck, Jack. Oh, let's get some food. I think I said let's get some food. Let's get some food. I'm hungry. I'm hungry. We got food. Yeah, actually, I think it's fine. I want to put some butter on my bread, but that's okay. Let's take a little bit of time. Just eat real quick before we try it. Actually, I think since we're just watching, I might just eat. I should talk, right?
Cistronic, on the other hand, those words interchangeably. Monocistronic, on the other hand, is where you've just got one gene per transcript so that each transcript results in one protein. So again, prokaryotes can do this or this. Eukaryotes are only monocistronic. Prokaryotes and eukaryotes also have different types and numbers of polymerase enzymes. Now here we're talking about RNA polymerases. Remember that DNA polymerases are enzymes that replicate DNA during DNA replication. So they copy the DNA to make more DNA. RNA polymerases use the DNA as a template to make RNA. And so RNA polymerase enzymes are the main enzymes of this transcription process. So prokaryotes and eukaryotes have different types and numbers of polymerases. Prokaryotes have one polymerase, RNA polymerase. It only works when it has a cofactor like molecule that's called sigma. Different sigmas can make the one RNA polymerase transcribe different genes. On the other hand, eukaryotes have three different polymerases known as RNA polymerase 1, RNA polymerase 2, and RNA polymerase 3. And they also transcribe a different subset of genes, specifically genes for mRNA, which go on to be expressed as proteins, but then also genes for tRNAs, which carry amino acids to the ribosome in translation, and genes for rRNA, which is the RNA that helps make up those ribosomes. All of these different types of RNA are being transcribed by slightly different polymerases in eukaryotes. Prokaryotes and eukaryotes also have different promoter elements. Now, I'm not going to go into a ton of detail on this, but basically, there are promoter elements, usually that are upstream of a gene, meaning like before the gene starts, every once in a while downstream of the gene, meaning after it ends. These promoter elements are just elements that are part of the nucleotide sequence in the regions surrounding the gene that are where the polymerase will bind or where like initiation factors will bind to get transcription up and started. And so prokaryotes and eukaryotes have different promoter elements. They use different sequences in different places to carry out that function. They also have different termination processes. So this is referring to the ending of transcription. So basically when you transcribe the mRNA and you get to the end, termination has to happen. In eukaryotes, there are a variety of termination factors that come in to make sure that the RNA polymerase lets go of the DNA and that the mRNA can then go off and be translated. In prokaryotes, there's a protein called Rho, R-H-O, that often plays a role, although there are also Rho-independent termination processes where Rho does not factor in. But again, they've just got prokaryotes and eukaryotes have some differences in their termination procedures and in the different kinds of proteins that play a role in that. Eukaryotes also modify their mRNA transcripts in three major ways. So when the transcription process ends in eukaryotes, we then have what's known as pre-mRNA. And that's because for it to become mature mRNA, it goes through something called post-transcriptional modifications. So modifications that happen once the transcription has ended. And so here are these three ways. One of them is the addition of a 5' cap. The 5' cap has to be put on. That helps to target the mRNA out of the nucleus, out through a nuclear pore, and helps the ribosome basically find the mRNA so it can dock onto it to proceed with translation. There's also getting a 3' poly A tail. So this is when a whole bunch of adenines, that's the A, so multiple adenines, poly A means multiple adenines. Multiple adenines are just tacked on to the end of the mRNA. And that's to protect the mRNA. Because once it exits the nucleus through a nuclear pore and goes out into the cytoplasm to be translated, there are proteins out in the cytoplasm that will actually degrade RNA. They'll chew it up and they eat it from the 3' end. And so since the 3' end has this poly A tail on the end of it, the enzymes can chew up that poly A tail without actually disrupting the nucleotides of the actual mRNA sequence that are coding for protein. So it's a protective mechanism. There's also something called splicing. This is where there are certain sequences of the pre-mRNA transcript known as intervening sequences or introns. And these get spliced out, they get removed. And then what's left are these sequences that are going to be expressed sequences, we call these exons, where the X comes from express, and those get joined together. And as a side note, eukaryotes can also do something that's called alternative splicing, which is basically where different exons can be spliced in or out so that you can have different polypeptides that are distinct structurally but related to each other because they have some of the same exons, and they can come from the same gene, just depending on which exons are kept and which ones are spliced out. And so the mRNA transcript goes through these three processes before it then goes on to translation. On the other hand, prokaryotes, they don't do any of these three things. Instead, they couple transcription and translation. That just means that transcription and translation occur simultaneously. In other words, translation, which is making polypeptides from the mRNA template, that can begin before transcription ends. And that's depicted here. We've got our DNA in green, our polymerase is right there. That's the RNA polymerase making the mRNA shown in black. We've got our ribosomes in blue. When there's multiple ribosomes in a line like that, it's actually referred to as a polyribosome. Remember, poly means many. And each one of them is making polypeptides, and those are shown here in pink. And so what you see here is that translation of the mRNA has started before the RNA polymerase is even done making the mRNA.
Wow.
So that's coupling. And prokaryotes can do that, of course, because they don't have a nucleus. So with eukaryotes, transcription happens in the nucleus. You have these modifications happen. Then the mature mRNA goes out into the cytoplasm where then translation begins. And prokaryotes, they don't have a nuclear membrane. And so the DNA and the ribosomes can be near each other. And so you can have these two processes be coupled together. If you're interested in learning more about how prokaryotes couple transcription and translation, I've got a separate video that goes into more detail on that. I also have a separate video that goes into a lot more detail on alternative splicing if you'd like to learn a little bit more about that one.
It probably is, but I think I'm okay.
I also have a video on comparing the process of DNA replication in prokaryotes and eukaryotes. So check that one out too if you're interested. And thanks for watching Biology, Professor.
Thank you, Dr. Holden.
The next several lectures, we're going to begin our discussion on the process of protein synthesis, also known as translation. Now, recall that DNA molecules, although they do carry and store the genetic information that is needed for protein synthesis, the DNA molecules themselves are not actually directly involved in protein synthesis. So what happens is the genetic information that is stored in DNA is transferred, is passed down to RNA molecules. And it's the RNA molecules that are directly involved in protein synthesis that takes place in the cytoplasm of the cell. Now, remember, there are 3 different types of RNA molecules that we should be aware of. And each one of these RNA molecules serves its own specific function. Now, let's recall what these RNA molecules are and what their function is. And let's begin with the messenger RNA. So the messenger RNA, also known as the mRNA, is basically the molecule that carries the genetic information from the nucleus into the cytoplasm of the cell. And it's the mRNA molecule that is used as a template by the ribosomes to synthesize our polypeptide chain, our protein. Now, the second type of RNA molecule that we should be aware of is the ribosomal RNA, or rRNA. Now, rRNA is synthesized in the nucleolus of the cell, and once synthesized, it travels into the cytoplasm through the nuclear.
Oh, he speaks so beautifully. Like, he really breaks it down for like, you know?
Pores of the nuclear membrane of the cell. Now, basically, the rRNA is its
Man speaks very matter of fact. He's confident in what he's talking about.
itself synthesized. It travels into the cytoplasm through the nuclear pores of the nuclear membrane of the cell. Now, basically, the rRNA is itself a constituent of the ribosome. So ribosomes are composed of protein. And once now rRNA is synthesized in the nucleolus of the nucleus of the cell, and once synthesized, it travels into the cytoplasm through the nuclear pores of the nuclear membrane of the cell. Now, basically, the rRNA is itself a constituent of the ribosome. So ribosomes are composed of proteins as well as rRNA. And the final type of RNA molecule that we should be aware of is transfer RNA, or tRNA. So tRNA is also synthesized in the nucleus, and the function of tRNA is to basically collect and bring the proper amino acids from the cytoplasm and into the ribosomes, so the ribosomes can use those amino acids to synthesize the polypeptide chain. Now, before we actually examine the process of translation, let's discuss what ribosomes actually are and what they consist of. So translation, or the process of protein synthesis, basically involves these special cell machineries known as ribosomes. And any given ribosome itself consists of a small unit and a large unit. So we have the small subunit and a large subunit. So together, a ribosome consists of 2 subunits. Now, these subunits are basically composed of proteins as well as rRNA molecules. So the rRNA molecules are created within the nucleolus, and then they are brought into the cytoplasm. And in the cytoplasm, as we'll see in just a moment, the 2 subunits, the large and the small subunits, combine with our mRNA to form our ribosome. Now, both prokaryotic and eukaryotic organisms contain ribosomes, but in eukaryotic and prokaryotic organisms, our ribosomes are slightly different. So they consist of slightly different small and large subunits. So let's take a look at the differences between our subunits. So let's begin with eukaryotic organisms. So in eukaryotes, our small subunit is the 40S, while the large subunit is the 60S, and they combine to form a unit known as the 80S unit. Now, in prokaryotic organisms, the small subunit is the 30S, and the large subunit is the 50S, and they combine to form the 70S unit. Now, the question that you might be asking is, what exactly is the S? What does the S actually stand for? Well, S basically stands for the Svedberg unit. And this is basically a unit that measures the rate at which the given particle or molecule, in this case, our subunit, sediments. So the Svedberg unit usually refers to how quickly something sediments or travels along or down a test tube that is basically rotating with some angular velocity. And the Svedberg unit is directly related to the mass of our particle, and it also depends on the size and the shape of the molecule. So heavier molecules will be found farther down the test tube than lighter molecules. So we see that the larger subunits, the 60s and the 50s, will be found farther down our test tube than the 40s and the 30s, because the 60s and 50s are basically heavier molecules. Now, what exactly is the purpose of these small and large subunits? Well, basically, before our translation actually takes place, the small and the large subunits are separated. They only come together during the process of translation, as we'll see in just a moment. And the purpose of our ribosome, so basically the large and the small subunit combine to form the ribosome, and the purpose of the ribosome is to basically translate the sequence of nucleotides into the proper sequence of amino acids. And this is exactly what we mean by translation. So the ribosomes basically translate the language of the mRNA into the language of our protein, and thereby synthesize our proteins by using our genetic code. So now, our process of translation can be broken down into 3 stages. We have the initiation stage, we have the elongation stage, and the termination stage. In this lecture, we're only going to focus on our initiation stage. So once our precursor mRNA or pre-RNA actually undergoes the proper post-transcriptional modifications in the nucleus, it basically becomes the mRNA, and it leaves the nucleus via the nuclear pores. Now, once it enters the cytoplasm, special types of proteins that are known as initiation factors basically help the mRNA find the small subunit. And the small subunit binds to the 5' end of our mRNA. And once the small subunit binds to our 5' end, it begins to travel along our mRNA until it locates a specific sequence of nucleotides that is known as the start codon. And this sequence is beginning with the 5' end, A, U, G, and ending with our 3' end. So basically, this is described in the following diagram. So once our mRNA is inside the nucleus, a set of proteins known as initiation factors help our small subunit locate the 5' end of our mRNA. And once it binds, it travels along our mRNA until it locates our start codon, the sequence AUG. And once it locates the AUG sequence, our small subunit basically tells its signals a tRNA molecule to go out and find a methionine molecule, and it brings our tRNA brings that methionine molecule to our AUG. So this is our tRNA molecule. It contains the complementary sequence to our AUG. So if this is the 5' end and this is the 3' end, we have AUG, then this is the 3' end, UAC, and this is the 5' end. And so once our small subunit locates the start codon, this basically goes out and finds our methionine, which is shown in orange, and then it brings our methionine to this location. And once our tRNA combines with this region, our large subunit also combines with the small subunit. And so we form our ribosome molecule. And this concludes the process of initiation. And the site, the location of our tRNA molecule inside the ribosome is known as the P site. In the next lecture, we're going to discuss the next stage known as elongation and the final stage known as termination. And we'll see that there are two other important sites that exist inside our ribosome known as the A site as well as our E site. So we see that the process of translation involves three types of RNA molecules. We have mRNA, tRNA, and rRNA. And basically what happens during the first stage of translation is our mRNA locates our small subunit, which then basically finds our AUG start codon sequence. And once it finds, it signals a tRNA to pick up the methionine amino acid and bring it into our small subunit. And once that binding takes place, it signals the large subunit shown here. So this is the small, this is the large unit. It tells the large subunit to basically attach to the small subunit, and that forms the ribosome, and that concludes the process of initiation.
The messenger RNA molecule. After transcription initiates and RNA polymerase is located on a molecule of DNA, now we have to talk about the second step, which is elongation of the growing transcript, the messenger RNA molecule. So as RNA polymerase is moving along the template strand of the DNA. RNA polymerase itself separates the two strands of the DNA molecule so that you have one strand that's called the template strand. The second strand we refer to as the coding strand. And RNA polymerase reads the nucleotide that's here and incorporates the complementary nucleotide there. And this growing strand of RNA exits a hole in this protein, and the end of the transcript, that's the part of the messenger RNA molecule that was synthesized first, exits RNA polymerase and is floating around in the nucleus where this transcription step is happening. This is prokaryotic elongation. And we're going to see that in eukaryotic elongation, there's not much of a difference between this step. Eukaryotic initiation and elongation look fairly similar in this regard. One thing that's different about prokaryotes, though, about eukaryotes, is that as soon as this end of the transcript comes out of RNA polymerase, it gets a 7-methylguanosine cap added. And 7-methylguanosine is a special type of nucleotide. It's a G, essentially, except that it involves a 5' to 5' linkage. That is, the 5' end of the G is stuck to the 5' end of the transcript. And there's a specific reason for this, and that's that this 5' cap, it's called, we refer to that as the 5' cap. And that protects the 5' end of this single-stranded molecule of RNA from being degraded. That's one way that the cell controls how much of this gene gets transcribed and how much transcript, how many messenger RNA molecules can accumulate to be then translated into proteins. Part of that process is protecting this RNA molecule from undergoing rapid degradation. So the next step in this process would be RNA polymerase moves along the template strand. So let's say that the template strand has this sequence, and that would mean that the coding strand of DNA is its complement, as we know. So when RNA polymerase starts here and reads in this direction and winds up here, it's reading the template strand. And there's no way to know in advance which strand RNA polymerase is going to use as the template strand. But the template strand is the strand that the RNA polymerase molecule is creating base pairing with. So we know that the RNA sequence is going to be complementary to the template strand. The RNA that's produced here is going to have the sequence U, because we know that there are U's in RNA and not T's, except that's complementary to the T. So that actually should be an A. Here we have A base pairs with U.
If it's complementary to the T, then yeah, we'll have a U on the coding where it's T. Yeah, that's right.
U in the RNA language. A, C.
A, C, G,
G,
T,
U, A.
Oh, sorry. A, C, G, yeah, U, A.
So the key point here is that an RNA molecule is going to be identical in sequence to the coding strand, because both of those, the RNA molecule and the coding strand, are both complementary to the template strand. And that's how you tell, when you're given the sequence of a messenger RNA molecule, which strand is the template strand and which was the coding strand. The RNA and the coding strand will match in sequence.
Right.
There's going to be one difference, though, and that's in the polarity of the molecules, and we'll talk about that in class. Now, something else happens in eukaryotes, aside from the addition of that 7-methylguanine cap. And those two things are splicing and polyadenylation. And we're going to talk about splicing next, but now I want to talk about termination. So how does RNA polymerase know when to stop transcription? We've looked at how RNA polymerase starts transcription initiation. How does it know where to stop? big difference between prokaryotes and eukaryotes. In a prokaryote, as that RNA polymerase molecule is moving down a double-stranded piece of DNA and generating that primary transcript, the RNA molecule. In prokaryote, there's a section of the gene, the DNA, that will encode a section of the RNA that will form a hairpin, which we've already talked about in class before. So there's a particular DNA sequence at the 3' end of every gene that will cause that RNA molecule, after it exits RNA polymerase, that hairpin will actually physically interact like a lock and key almost with RNA polymerase. And that causes RNA polymerase to literally practically fall off of the DNA molecule, and that stops transcription. RNA polymerase is no longer attached to the DNA molecule. Eukaryotes do things a little bit differently in this regard, transcription termination. In this case, as RNA polymerase is, again, moving down the DNA molecule, producing a transcript, there's going to be a section of the gene that encodes a specific sequence. In the RNA, it's AAU, AAA. That's the polyadenylation signal sequence.
Gotcha. Yeah. On the 3'.
And what that does is it's located about 200 or 300 base pairs upstream of the very end of the transcript. And this sequence gets recognized by another protein that's associated with RNA polymerase. When that protein reads that sequence in the RNA molecule, AAU, AAA, a different protein comes in and cuts the transcript off of RNA polymerase. And that happens about 20 base pairs, 20 nucleotides downstream towards the 3' end, and releases this RNA molecule. So now you have an RNA molecule that's floating around in the nucleus that has that signal sequence, and then about 20 more nucleotides. And by the way, what's up here? That's the 5' end, and it's going to have the 7-methylguanine cap on it. The last step in eukaryotic transcription termination is that at the very 3' end of the transcript, after it gets cut about 20 nucleotides downstream of that poly A signal sequence, the enzyme poly A polymerase does exactly that. It polymerizes or adds poly A, a string of A's, to the end of that transcript. And this is called the 3' tail, or the poly A, mini A tail. And that's how transcription terminates in eukaryotes.
Gotcha. Thanks, Joseph. Sure. I guess we'll read it. I think I read it before. I don't know if you guys can even see that. It's too far. My glasses now.
here. Solve this stuff, right? Nope, wrong color. Okay. You have translation occurrence. We talk about chromosome. So you could say that this chromosome right here, this chromosome your father has one chromosome. Now you have individual chromosomes, but that.
Oh, 4 questions to the exercise. Isn't it 2n? Oh, it was. That's I messed that one up. Didn't read it. I want to say 2 chromosomes. This is 1 chromosome, 2 sister chromatids, and then this is 2 chromosomes. Wait, D?
Let's talk a little bit about DNA cloning. Identical copies of a piece of DNA. And usually it's a piece of DNA that codes for something we care about. It is a gene that will express itself as a protein that we think is useful in some way. Now, you might have also heard the term cloning in terms of the Clone Wars and Star Wars, or Dolly the sheep. And that is a relic draw, the two strands, just so we remind ourselves. But when we talk about cloning and DNA cloning, we're talking about something a little.
Use the bathroom. We'll continue. Do this one. DNA repair 1 and 2 again. Maybe we might as well reread this, right? And then we'll read this one as well. Maybe do the questions, and then we'll just watch the rest of these, and then do Anki. We're almost there. We're almost there. We're almost there. Why does it keep going? Just go here. Stay on here. We're back. Use the restroom. go. Okay, let's finish this up. I don't know if this is my third session.
A little bit similar, although as you'll see, it's still quite fascinating. It's identical copies of a piece of DNA. So how do we do that? Well, let's say that this is a strand of DNA right over here, and I'm just drawing it as a line, but this is a double-stranded, and I'll just write it down. This is double-stranded. I don't want to have to take the trouble of keep drawing the multiple strands. Actually, let me just try to draw the two strands, just so we remind ourselves. So there we go. This is the double-stranded DNA, and let's say that this part of this DNA has a gene that we want to clone. We want to make copies of this right over here. So gene to clone, gene to clone. Well, the first thing we want to do is we want to cut this gene out somehow. And the way we do that is using restriction enzymes. And there's a bunch of different restriction enzymes. And I personally find it fascinating that we as a civilization have gotten to the point that we can find and identify these enzymes, and we know at what points of DNA that they can cut. They recognize specific sequences. And then we can figure out, well, which restriction enzyme should we use to cut out different pieces of DNA? But we have gotten to that point as a civilization. So we use restriction enzymes. We might use one restriction enzyme, use a different color here, that latches on right over here and identifies the genetic sequence right over here and cuts right in the right place. So that might be a restriction enzyme right over there. And then you might use another restriction enzyme that identifies with the sequence at the other side that we want to cut. So let me label these. Those things right over there, those are restriction enzymes. Restriction enzymes. And so now you would have, after you apply the restriction enzymes, you will have just that gene. You might have a little bit left over on either side, but essentially you have cut out the gene. You've used the restriction enzymes to cut out your gene. And then what you want to do is you want to paste it into what we'll call a plasmid. And a plasmid is a piece of genetic material that sits outside of chromosomes, but that can reproduce along, or that could, I guess we could say, can replicate along with the machinery of the genetic machinery of the organism, or it can even express itself just like the genes of the organism that are in the chromosomes express themselves. So this is where we cut. Let me write this. We cut out the gene, and then we want to paste it. Then we want to paste it into a plasmid. And plasmids tend to be circular DNA. So we will paste it into a plasmid. And in order for them to fit, there's oftentimes these overhangs over here. So you might have an overhang over there. You might have an overhang over there. And so the plasmid that we're placing in might have complementary base pairs over the overhangs, which will allow it will become easier for them to react with each other if they have these overhangs. So we're pasting it into the plasmid. And this is amazing because obviously DNA, this isn't stuff that we can manipulate with our hands the way that we would copy and paste things with tape. You're making these solutions and you're applying the restriction enzymes. The restriction enzymes are just in mass cutting these things. They're bumping in just the right way to cause this reaction to happen. Then you're taking those genes and then you're putting them with the plasmids that happen to have the right sequences at their ends so that they match up. And then you also put in a bunch of DNA ligase to connect the backbones right over here. And we also saw a DNA ligase when we studied replication. So that is DNA ligase, which you can think of it as helping to do the pasting. And so now we have this plasmid, and we want to insert it into an organism that can make the copies for us. And an organism that's typically used or a type of organism is bacteria, and E. coli in particular. And so what we could do is let's say that we have let's say you have a vial right over here. You have a vial, and it has a solution in it with a bunch of E. coli. You actually wouldn't be able to see it visually, but there's E. coli in that solution. And then you would put your plasmids, which would be even harder to see, in that solution. And somehow we want the E. coli, we want the bacteria to take up the plasmid. And the technique that's typically done is giving some type of a shock to the system that makes the bacteria take up the plasmids. And the typical shock is a heat shock. And this isn't fully understood how the heat shock works, but it does. And so people have been using this for some time. So if you have a bacteria right over here. It has its existing DNA. So this is its existing genetic material right over there. Let me label this. This is the bacteria. You put it in the presence of our plasmids. So you put it in the presence of our plasmid, and you apply the heat shock, and some of that bacteria is going to take in the plasmid. It's going to take in the plasmid. And so just like that, it's going to take it in. And so what you then do is you place the solution that has your bacteria, some of which will have taken up the plasmid, and you put it, and then you try to grow the bacteria on a plate. So let me draw that. So here we have a plate to grow our bacteria on. And it has nutrients right over here that bacteria can grow on. It has nutrients. And so you could say, okay, we'll put this here, and then a bunch of bacteria will just grow. So you would see things like this, which would be many, 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 many cells of bacteria. There would be colonies of bacteria. You could just let them grow. But there's a problem here, because I mentioned some of the bacteria will take up the plasmids and some won't. And so you won't know, hey, you know, when this bacteria, when it keeps replicating, it might form one of these, colonies. So this is a colony that you like. So this one is a good colony, put a check mark there. But maybe this colony is formed by a initial bacteria or set of bacteria that did not take up the plasmid. So it won't contain the actual gene in question. So you don't want that one. So how do you select for the bacteria that actually took up the plasmid? Well, what you do is, besides the gene that you care about, that you want to make copies of, you also place a gene for antibiotic resistance in your plasmid. So now you have a gene for antibiotic resistance here. And so only the bacteria, and I think it's amazing that we as humanity are able to do these types of things, but now only the bacteria that have taken up the plasmid will have that antibiotic resistance. And so what you do is, in your nutrients, you do nutrients plus antibiotics, plus an antibiotic. And so this one will survive because it has that resistance. It has that gene that allows it to not be susceptible to the antibiotics. But these are not going to survive. They're not even going to happen. They're not even going to grow because there's antibiotics mixed in with those nutrients. And so this is a pretty cool thing. You started with the gene that you cared about. You cut and pasted it into our plasmid. Let me write the labels down. Into our plasmid. That also contained a gene that gave antibiotic resistance to any bacteria that takes up the plasmid. You put these plasmids in the presence of the bacteria. You provide some type of a shock, maybe a heat shock, so that some of the bacteria takes it up. And then the bacteria starts reproducing. And as it reproduces, it also is reproducing the plasmids. And because it has this antibiotic resistance, it is going to grow on this nutrient antibiotic mixture. And the other bacteria that did not take up the plasmid, bacteria. Now, the next one, say insulin for diabetics. Well, you could actually use that bacteria's machinery, use its reproductive machinery are not going to grow. And so just like that, you can take this colony right over here and put it into another solution or continue to grow it, and you will have multiple copies of that gene that are inside of that bacteria. Now, the next question, and I'm oversimplifying things fairly dramatically, is, well, how do you now have a bunch of bacteria that have a bunch of copies of that gene? How do you make use of it? Well, the bacteria themselves, let's say that gene is for something you want to manufacture, say insulin for diabetics. Well, you could actually use that bacteria's machinery. We use its reproductive machinery to keep replicating the genetic information, but you can also use its productive machinery, I guess you could say. It's going to express its existing DNA, but it can also express the genes that are on the plasmid. In fact, that's what gives that's what would give the bacteria its antibiotic resistance. But if this gene was, say, for insulin, well, then the bacteria will produce a bunch of insulin molecules, which you might be able to use in some way. And I'm not going to go into all of the details of how you will get the insulin out and how you can make use of it, but needless to say, it's pretty cool that we could even get to this point.
Sure. All right, let's read this one, dude. Let's take a break. We're nearly there, and then I think this almost gets us. Well, pretty much almost gets us back to just watching videos. And the videos don't seem that long, so we should be studying Anki like I'd probably say within the next hour or two. Maybe before the end of the day, we can at least do like. I think maybe we can do 2. Or we might be able to do 3. I don't know. Maybe just 2, and then we'll call it. We'll see. Let's go back. So we were here. We have to read this when I come back. Anyone have any questions? Questions, comments, concerns, anything they want to add? Anything you think that I should be doing on top of what I'm already doing? We have 11 weeks. 11 weeks of content to review and 5 full and practice exams, each 8 hours to take. Probably after this one, I'll take another one before the test, like just 2 days later. Yes. All right, guys, I'll be right back. Let me just put this downstairs then. And maybe, since I'm feeling sleepy, we'll probably take another B12. We'll take another B12. And maybe on some of these videos, we'll do a little bit of workout just so I can get the butt flowing or not. I don't feel so tired. So honestly, right now, I feel like I want to go to sleep. But I can't. I got too much work to do. Too much work to do to go to sleep now. Okay. Let's continue. I don't know what it is. I think I want this jacket. Switch it up. Yeah, we're back. Continue.
DNA that's in the process of being replicated. And I want to focus in. Let's take a look at a segment of DNA that's in the process of being replicated. And I want to focus in particular on the enzyme that replicates DNA. And that enzyme is DNA polymerase. And actually, there are a few different types of DNA polymerases, and the one that we're looking at right now is DNA polymerase 3. So DNA polymerase 3 synthesizes new DNA, and it also has the ability to proofread or kind of check the DNA that's putting together and make sure that there are no mistakes in it. But before we get into that, let's just orient ourselves and quickly summarize the diagram that we're looking at. So this enzyme over here is DNA helicase. That's the enzyme that unwinds the double-stranded DNA so that DNA polymerase can then come in and start replicating. Right over here, you can see I drew the backbone in a different color. That's the RNA primer. Now let's just label the DNA strand that's being synthesized. It's synthesized from 5' to 3'. And actually, the bottom strand of DNA is synthesized in the same time as the top strand, but I just left that out of the drawing to keep things simple. And let's say that the yellow bases represent the nitrogen-based thymine. Let's say that the orange bases represent cytosine. The green ones represent adenine. And the blue ones represent guanine. And so thymine and cytosine are the pyrimidines. They are composed of a single ring structure. So they're made up of one ring that has 6 sides to it. And then adenine and guanine are the purines. They are a double ring structure. So they're composed of one ring with 6 sides to it, and then that ring is attached to another ring that has 5 sides to it. And actually, these structures are a little bit more complex. There are other atoms, in it, and there are some double bonds, but we're just going to keep things simple for now and leave it at that. And so let's get back to our DNA that's being replicated. Right over here, I left a space. I didn't put the nucleotide in. And let's say that by accident, instead of it being paired up with the proper base, which is adenine, it accidentally gets paired up with a guanine. So that's a mistake. And DNA polymerase 3 actually has the ability to sense if it made a mistake. And if it does realize that, it's going to go backwards, and it's going to actually remove the incorrect base and replace it with the correct base. So let's do that. It's going to remove the incorrect base and replace it with the correct one. Of course, remember the nitrogen base is attached to the sugar backbone. And so this activity that I just described to is called exonuclease activity. And so nuclease tells us that means the ability to remove a nucleotide. And exo, just going to underline that. So exo tells us that it can remove a nucleotide, but only from the end of a DNA strand. So it was able to remove the nucleotide because it was at the end of a strand. This is in contrast to endonuclease activity. So an endonuclease can actually remove a nucleotide from the middle of a DNA strand. So it would be able to remove, a nucleotide from like right over here, for example. And just keep that in mind because we're going to come across some endonucleases as well. Anyway, back to our exonuclease activity. If we want to be more specific, the exonuclease activity of DNA polymerase 3 is actually 3' to 5' exonuclease activity. And the reason it's called 3' to 5' exonuclease activity is because when DNA polymerase 3 makes that correction, it has to move backwards in the 3' to 5' direction in order to do that. There's another enzyme, DNA polymerase 1. I'm just going to abbreviate polymerase with POL. And DNA polymerase 1 also has exonuclease activity. And DNA polymerase I is actually the enzyme that will remove the RNA primer at the end of replication. And just as a side fact, the exonuclease activity of DNA polymerase I is actually in the 5' to 3' direction. So if you want, you just keep that in mind. And so DNA polymerase 3 and DNA polymerase 1 are both able to repair or fix mistakes that happen during DNA replication. And just to give you some perspective as to how often this occurs with and without repair. So normally we'll have a mistake happening in replication between 1 in 100,000 bases to 1 in 1 million bases. That's normally the amount of mistakes that would occur. But with the repair mechanisms of DNA polymerase 3 and DNA polymerase 1, this is reduced to a mistake that happens once in about 100 million bases. And so they are very, very effective at lowering the error rate in DNA replication. So the next question I want to ask is, what if this mistake over here was somehow not corrected during replication? Maybe there was something wrong with one of the enzymes, something happened, and that mistake was actually sustained. So let's take a look at that. So here's a piece of DNA with our mistake incorporated into it. And so before we discuss if this mistake can be corrected or not, let's see what happens if this mistake is not corrected. So right here we have our original DNA, and we're replicating it. And let's just say that this strand over here is the same as that strand. Let's say that the bottom strand in the original DNA is the same as this strand. And so let's look first at the newly replicated DNA on the left. So we have right over here the thymine base, and assuming DNA was replicated properly, it's going to have an adenine complementary to it. Now let's take a look at the DNA on the right. So on the bottom we had a guanine, and it's going to be paired up, hopefully with the correct base, which is a cytosine. Now let's just quickly look back at our original DNA. We were supposed to have a thymine with its complementary adenine. And actually, that's exactly what we got over here. Just gonna circle it. So this DNA is actually the correct sequence. But look at the DNA over here on the right. This is not correct. This is a mutation. And this is an example of how mutations can occur if the DNA repair mechanisms are not working properly. And so let's go back to our original question. Can we fix the original mistake so that this mutation does not occur? And the answer to that question is yes. So the mismatch repair mechanism. And the mismatch repair mechanism is composed of a number of proteins. And the first thing these proteins are going to do is they're going to recognize if there's a problem. And the reason that they're able to recognize the problem is that when you have a mismatch in DNA, it tends to distort the sugar backbone a little bit. And they're going to mark the area with a cut. So they're going to cut the incorrect base or mark it with a cut. The next thing that's going to happen is an exonuclease is going to remove the incorrect nucleotide. So we're going to remove the incorrect nucleotide. The next step is one of the DNA polymerases is going to insert the correct nucleotide. So we're going to pair our thymine up with adenine. And the last step is a DNA ligase is going to connect the nucleotides on its sides, and also to its complementary nucleotide on the other strand. And I'm actually going to just correct that distorted sugar backbone. And so here's our repaired DNA. And just to clarify, the mismatch repair mechanism that we're talking about here happens after replication. The repair is done by DNA polymerase 3 and DNA polymerase 1 that we discussed before. That happens during replication or at the end of replication. And so one thing you might be wondering is, how does the mismatch repair mechanism know to distinguish between the original parental strand and the newly synthesized strand that has the mistake on it? In other words, how does it know which base over here is correct? In our case, that's the thymine, and which one is incorrect? In our case, well, it was a guanine. And we know the answer to that question in bacteria. So in bacteria, the parental strand will have adenines that are methylated. So I'm just going to draw some methyl groups on all the adenines. And that allows the mismatch repair mechanism to kind of recognize and distinguish between the original strand that has the correct base on it and the new strand that has the incorrect base on it. But we're not quite sure how the mismatch repair mechanism in eukaryotic cells and in other prokaryotic cells knows to distinguish between the strand that has the correct nucleotide and the strand that has the incorrect nucleotide. There are certain things that can cause damage to the structure of DNA. And one example of that is UV rays. And so before we get into the damage that UV rays cause, let's just focus for a second on the key that I drew here on the left. And it's just to help us remember which colors represent which nitrogen bases. So yellow represents the nitrogen-based thymine, the orange bases represent cytosine, the green bases represent adenine, and the blue bases represent guanine. And so back to our DNA that's being damaged. If you look over here, there are two thymine bases that are kind of stuck together. And that's called a pyrimidine dimer. So a dimer is simply when you have two molecules that are identical, they're stuck to each other. And pyrimidine tells us that it can be two thymines that are stuck together, or it can be two cytosines that are stuck together. And UV rays cause the formation of pyrimidine dimers. And so you can see that the pyrimidine dimer actually is causing the sugar phosphate backbone to protrude or kind of stick outwards. And not just that, but because the backbone is sticking outwards, the bond between this cytosine and this guanine snapped. So you can see that there's some structural damage that happened to the DNA. And so what are some factors that can cause damage to DNA? And I want to just make a clear distinction between a mutation and DNA damage. So it's not the same thing. A mutation is when you have a change in the sequence of DNA. So for example, if we had a piece of DNA that read A, T, C, G, and then something happened and it read A, C, G. So this A is in the wrong place. That is a mutation. But when we talk about DNA damage, we're talking about damage to the structure of DNA, but the nucleotides are actually in the correct order. And so DNA damage can be caused by endogenous or internal factors, and that means factors that originate within us, within our own cells. So for example, there are certain byproducts of metabolism that can cause DNA damage. Or DNA damage can be caused by exogenous or external factors, and those are factors that originate outside of us or outside of the organism that we're discussing. So let's start with exogenous factors first. So we spoke about one of them, UV rays. And there are a lot of exogenous factors that cause DNA damage, or just to list a few. Gamma rays can cause DNA damage, X-rays, and so that's why it's not healthy to be exposed to a lot of these rays. And Now let's talk about some endogenous factors. So reactive oxygen species is an example of an internal factor that can cause DNA damage. And reactive oxygen species are molecules that contain oxygen and they're highly, highly reactive. So there are a lot of different kinds of reactive oxygen species, but we're just going to give 2 examples. So for example, a superoxide anion, which is O2 with a negative charge. So let's just draw that. It's 2 oxygen atoms that are bound together, but there is 1 extra electron. And I'm actually going to draw the extra electron in a different shade of purple. And so this whole molecule has a negative charge. So that's a reactive oxygen species. Another example would be peroxides. So peroxides are molecules that have 2 oxygens, and on either end there's another atom. So that R can represent different types of atoms. So this is the general way that peroxide looks. You might have heard of hydrogen peroxide. So this is hydrogen peroxide. And so where are these reactive oxygen species in our cells coming from? So actually, reactive oxygen species are a normal byproduct of the electron transport chain in the mitochondria. So there are a lot of reactive oxygen species all over our cells. But fortunately, we have many enzymes that help protect against the damaging effects of reactive oxygen species. And you may have heard of the term antioxidant. And so an antioxidant is a molecule that also helps protect us against the damaging effects of reactive oxygen species. You may have heard that certain foods are really healthy because they have a lot of antioxidants, and that's true. So vitamin C, for example, is an antioxidant. Vitamin E, and there are many different types of antioxidants, but we're just going to give these 2 as an example. And so now that we've discussed some of these sources of DNA damage, let's go back to our damaged DNA and see if there's a way to fix this. So our cells can get rid of these pyrimidine dimers in a process called nucleotide excision repair. And so the first step in nucleotide excision repair is an enzyme, an endonuclease process called if there's a way to fix this. And so we're just going to give these 2 as an example. And so now that we've discussed some of these sources of DNA damage, let's go back to our damaged DNA and see if there's a way to fix this. So our cells can get rid of these pyrimidine dimers in a process called nucleotide excision repair. And so the first step in nucleotide excision repair is an enzyme, an endonuclease, is going to remove the pyrimidine dimers and any other nucleotides that are kind of not the way they're supposed to be. And so I just want to pause for a second and analyze that word. So nuclease tells us that it's an enzyme that's able to cut out nucleotides, and that prefix endo tells us that it's able to cut out nucleotides from within a DNA molecule. That's in contrast to an exonuclease that can only take out nucleotides that are at the beginning or end of a DNA molecule. But anyway, the endonuclease is going to cut out the dimer and any other nucleotides that are not properly arranged. So let's just cut out all the nucleotides. The next step is a DNA polymerase. I'm just going to abbreviate that POL, is going to come and bring the nucleotides that belong there. And the last step is DNA ligase, is going to make sure that those new nucleotides are attached properly to the nucleotides on either side and also to the nucleotide that's complementary on the other strand. And so that was a mouthful. Let's actually just draw all of that. So let's get rid of our backbone that's kind of protruding and just not right. So let's redraw our backbone, something like that, or actually draw a little bit closer. And then DNA polymerase brings the correct nucleotides. But remember, it's the ligase that actually connects nucleotides properly. And so here's our corrected DNA. But what happens if for some reason the nucleotide excision repair is not working properly? And this repair mechanism is only one example. There are many different types of DNA damage that can occur in many different types of repair mechanisms. What happens if for some reason one of these or a couple of these are not working properly? Then we get a cell that has a lot of damaged DNA. And there are 3 things that can happen to a cell like this. The first is it might go into this dormant state where it just ages and does not divide anymore. That's called senescence. The second thing that might happen to it is what's called programmed cell death or apoptosis. And that basically means that the cell's going to commit suicide and die. And the third thing that might happen is the cell might start to divide uncontrollably. I'm going to write unregulated cell as an example of this. Melanoma as an end might start to so like for some reason, well, there are many different types of DNA damage that can occur in many different types of repair mechanisms. What happens if for some reason one of these or a couple of these are not working properly? 3 things that can happen to it, and this can cause cancer. As an example of this. Melanoma as an end. Melanoma happens when the nucleotide excision repair mechanism that we just discussed is not working properly. And so you have this accumulation of pyrimidine dimers that damages the DNA very much, and then the cell starts to divide uncontrollably.
I'll take a cold shower. Maybe it's just the heat, and that's maybe it's the heat that's draining my energy. So we'll take a cold shower, wake up. So I'm actually really slowing down. It's not that good. Ah, seriously. I'll be back. Hold on. Let's see, I think Mom might have sent me something. Look at it after the break. Were we here? Did we finish it? Oh yeah, we did finish it. Okay. If 10% are guanine and 10% are cytosine, and that means we have 40% adenine and 40% thymine. It's false. It's false. It's true. TT. TTGG. 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 Austrian. X-ray crystallography. In the diffraction pattern. Image 51. Uproar! Uproar! There's an uproar in I don't know, probably maybe. Maybe there's an uproar today. Today there'll be protests. How dare you use my data without permission?
A little bit about the actual.
Hold on, buddy. Okay, go ahead.
In this video, I want to talk a little bit about the actual details of the base pair hydrogen bonding, and I also want to talk about melting temperature. So, if you recall, the purines were pure as gold or pure as silver, and the purines were adenine and guanine, A and G. And the pyrimidines were cut the pie, right, or pyramids, that sharp edges that cut, so C, U, T, cytosine, uracil, thymine. Now, temperature. So, if you recall, the purines were pure as gold or pure as silver, and the purines were adenine.
Pure as gold or pure as silver. Oh, okay, for recall. Pure as gold. Pure as gold. What's with the S?
And guanine, A and G. And the pyrimidines were cut the pie, right, or pyramids, that sharp edges that
cut the pie.
Cut, so C.
Oh, cut the pie's pretty good.
U, T, cytosine, uracil, thymine. Now, when we also know that A's pair in DNA, A's pair with T's and C's pair with G's. So it's always a purine in pairing with a pyrimidine, and a pyrimidine, right, pairing with a purine. So this brings up this idea of Chargaff's rule. So this dude, Chargaff, he came up with this rule that the number of purines must equal the number of pyrimidines.
Okay.
So basically, the number of A's, right, purine, will equal the number of T's, and the number of G's will equal the number of C's. So it's always a purine pairing up with a pyrimidine in the base pairs. So each base pair is a purine and a pyrimidine. That's always the case.
Okay.
It's never a purine and a purine, and never a pyrimidine and a pyrimidine. That doesn't happen. That doesn't happen. And that makes sense, because if you recall, purines had 2 rings and pyrimidines have 1 ring. So basically, if you think about the length of the actual hydrogen bond, we have like a 2 rings plus 1 ring, right? If we had 2 purines, that would be 2 2-ring structures. That would be too long. If we had 2 pyrimidines, that would be too short. So if we have 1 purine and 1 pyrimidine, pairing up all the time, we always have essentially 3 rings total, and the DNA strand wouldn't have to, be wider at certain areas and shorter or narrower at certain areas. So I want to sort of draw out the actual hydrogen bonds between the groups here. So in an AT pair, we mentioned it before that there are 2 hydrogen bonds. So the way those 2 hydrogen bonds look is if we have here, this is an adenine, and this here is a thymine. So the hydrogen bonds, the 2 hydrogen bonds that exist between them are right here and right here. So here, this amino group is the H bond donor, and that carbonyl group, oxygen, is the H bond acceptor. Here, this N with the H on it is the H bond donor, and this here is the H bond acceptor. So these are the 2 H bonds in AT base pairs. In the case of GC base pairs, there are 3 H bonds, and the way those look is if you have this guanine base and this cytosine base, 3 H bonds exist right here. This is one of them. This is the other, and this is the third. Okay. You notice I wrote SP here, SP here, SP here, SP here. That just indicates sugar phosphate. So that's a sugar phosphate backbone. I didn't want to draw it all in. I just wanted to focus on the actual hydrogen bonds and how they look.
Mm-hmm.
So this brings me to the idea of melting temperature. So melting temperature, otherwise known as TM, is the temperature at which the DNA double helix separates into 2 strands. So if we have a single strand on the left side, and the right side is another single strand, they're held together by these H bonds. So if we want to melt those 2 strands apart, then we're going to have to break those H bonds. So what we can do is we can add heat, right? So what does the actual melting temperature depend on? The simplest thing I can say is it depends on GC content. Now, why is that? Well, AT base pairs have 2 hydrogen bonds. GC base pairs have 3 H bonds. So if we wanted to melt these 2 apart versus melting these 2 apart, what would be harder? Well, it's pretty simple, right? The GC base pair, because it has more H bonds, it would be harder to break apart. So if you have a DNA strand that has a higher GC content, then it would be harder to break apart, right? Harder to take those or melt those strands apart. So they will have a higher melting temperature. That makes sense, right? Just to give you a quick example, if you had 2 sets of double-stranded DNA, one set had, and they both have 100 base pairs. One of them has 70 GC base pairs, and the other has 30 GC base pairs. Which one would have the higher melting temperature? The one with the more GCs, right? The one with the 70 GCs. And that's just because it would require more heat to tear those 2 strands apart. Okay. Just to give you a quick visual, imagine this. So this is a DNA strand here, or a double-stranded DNA here. Now, if we add some heat, what's going to happen? If we add heat, we're going to begin to melt that strand apart. We're going to begin to melt these H bonds apart. We're going to break them up. And so the strands begin to come apart. If we add some more heat, eventually these strands will become single-stranded. We will have broken all of the hydrogen bonds. This process, you might have already heard the term associated with it. It's called denaturation or denaturation. It's going to happen. If we add heat, we're going to begin to melt that strand apart. We're going to begin to melt these H bonds apart. We're going to break them up. And so the strands begin to come apart. If we add some more heat, eventually these strands will become single-stranded. We will have broken all of the hydrogen bonds. This process, you might have already heard the term associated with it. It's called denaturation or denaturation. And that's really just melting the strands apart. So what if we wanted to bring the strands and put them back together? Well, we would have to, we want to, instead of add a heat, we would do the opposite of that. We would want to cool it down. So we'd cool it down, and eventually the strands would come back together. That process would be called renaturation. Another term associated with this is reannealing of the strands. So the strands would reanneal, they'd come back together. So I hope that was a helpful overview of what's going on with those bases. Southern California, feel free to contact me via email at moofuniversity@gmail.com and see the description below for more details. Thanks for watching.
Hi, it's Mr. Anderson, and in this podcast, I'm going to talk about DNA replication. That's the process by which DNA makes a copy of itself. Why is that important? Well, this right here is an egg being fertilized by a sperm.
I know. Hold on.
Hello guys, talking about. Hello guys, talking about.
From labor side.
That means it's about to become a zygote. It'll divide through mitosis to eventually create an embryo, a fetus, and eventually create a human. And that human is going to have billions and trillions of cells. And we have to make sure that each of those cells has the same exact DNA that was in that original cell. And we do that through the process of DNA replication. If we were to point specifically where that occurs, well, in eukaryotic cells, like this little baby here, that cell cycle basically is, remember, the G1 phase where it grows, the S phase where we copy all the DNA, the G2 phase where it continues to grow. So this whole process right here is called interphase. We then have mitosis where we go through prophase, metaphase, anaphase, telophase, cytokinesis. But right here, we have to make sure during that S phase that we copy all of the DNA. Now, mitosis is not found in prokaryotes, but they're going to use a process called binary fission. And if you look right here, here's their nucleoid region. They'll copy their DNA perfectly before they split in half. And so in all life on our planet, DNA replication is super important. And so basically, when they figured out the structure of DNA, 3 theories came about as to how it actually makes copies of itself. The first is semi-conservative, conservative, and dispersive. Watson and Crick actually believed in this. They believed that DNA would split in half, and then you'd copy new strands on either side. But there are other scientists who believe in a conservative theory that first DNA remains intact, and it kind of makes a photocopy of itself. And then some believe that there was kind of a combination of conservative and semi-conservative, that chunks of it were being split between the two. And this had to do with, they thought, the histone proteins and how the DNA wrapped around it. And so basically, the whole thing was figured out through the Michelson-Stahl experiment. Basically, what they used was 2 different types of nitrogen. Good old run-of-the-mill nitrogen-14, and then nitrogen-15, an isotope that's heavier than nitrogen-14. So basically, they bred a bunch of E. coli on nitrogen-15 until all of their DNA was nitrogen-15. They then put them on a broth of nitrogen-14 and basically a bunch of E. coli on nitrogen-15 until all of their DNA was nitrogen-15. They then put them on a broth of nitrogen-14 and basically in that first generation, if it would have been conservative, we would have had one band that would have been totally heavy at this N15 line and then one that was at N14. But instead, we got this intermediary amount of DNA. In other words, it was a mix of the two. And then through generation after generation after generation, they were able to figure out that this is how DNA copies itself. It copies itself semi-conservatively. And so to look at that in a little better detail, basically here is your DNA. It's a double helix. It will unzip in the middle. So you can see it's unwinding right here. And then we're going to add new strands on either side. So we eventually start with, we start with one strand, and we're going to end up with 2 strands. Each of these strands are identical to that first strand, and each of them are going to contain half of that original DNA. So again, it's semi-conservative in nature. Before we actually talk about the process of DNA replication, we should talk about DNA and the parts of DNA. Remember, DNA is going to have 3 parts to it. You're basically going to have a sugar. That would be this deoxyribose sugar right here. I could circle it. This is going to be our deoxyribose sugar. You're going to have a nitrogenous base attached to that. And then you're going to have a phosphate group. And so there are 3 parts to every nucleotide. Again, we've got a sugar and a phosphate and then a nitrogenous base. But you can see that there's going to be another nucleotide right here and another nucleotide going to be found right here. So let me clean that up a little bit. Because it's anti-parallel in nature. In other words, DNA runs next to each other, so it's parallel, but it's anti-parallel in nature. In other words, the 2 strands of DNA are actually running in opposite direction. And when I mean running, I mean chemically running in either direction. So basically, how do we tell which way it's going? Well, we do that based on the sugar. And so if we look at this sugar right here, the sugar is going to have a carbon here. So we call that carbon the 1' carbon. It's going to have a carbon right here, and we call that the 2' carbon. It's going to have a carbon right there. We call that the 3' carbon. It's going to have a carbon right there called the 4', and then it's going to have a carbon right here, and that's called the 5'. And so basically, if you look here, that whole thing is going to run from the, let's look way down here, 1 to 3' end. Oops, let me go back. So that's going to run from the 1 to 3' end right here, all the way up to the 5' end over here, because here's that 5'. If we look on the other side of the DNA, you can see it's running the opposite direction, from the 3' to the 5'. And that's going to be important when we look at DNA and how it copies itself. And so let's look at that. If we look on the next slide, in DNA replication, there are tons and tons and tons of enzymes that are helping out. It's way more complex than this, but from a diagram level, this is pretty good. So basically, the DNA is going to be a double helix in this direction, but we're going to have this enzyme right here. It's called helicase, and it's basically going to unwind the DNA. So we're going to go from this double helix to these single strands of DNA on either side. These strands are going to be held in place using these enzymes. They're called single-strand binding proteins. They're basically going to hold it in place. And so now we have that unwound DNA. The big enzyme that's super important in here is called DNA polymerase. So if we look on this side, DNA polymerase is going to race down the DNA, and it's going to add new nucleotides on the other side of the DNA. So here's the original strand. And you can see that DNA polymerase has already been here because it's added new strands in this direction. Now the trick is that we can only add new nucleotides on the 3' end. We can't add it on the 5' end. And so basically, again, so here's the 5' end. If we follow that right down here, we can add DNA on this side, on the 3' end, and it's just going to go on silky smooth. In other words, helicase unwinds it, DNA polymerase adds the new letters. And on this side, we call that the leading strand. Everything's going to be perfect. It's just going to flow on there perfectly. But the problem is, since we can only add DNA on the 3' end, we can't add it up here. We can't add it on the 5' end over here. And so what's evolved is this really elegant method called the lagging strand. So we can finish out the other side. And it's lagging strand because it tends to lag behind the other side. If you've done any sewing, which I never have, it's kind of like back stitching. In other words, you're going in this direction, but you're back stitching the way as you go. And so basically, there are a number of different parts that are found in here. First thing that we have to do is we have to put down a primer. And so there's going to be RNA primase, and primase is going to add down a primer. A primer is just one little bit of RNA. So we'll add a little bit of an RNA first. And after we've added that RNA primer, then DNA polymerase can go in this direction. So once the primer's in place, then we can run in that direction, we can run in that direction, we can keep running in that direction. So we got to put a little RNA down, then DNA polymerase goes. Unfortunately, it can't connect it here because we've got DNA bumping into RNA, and so there's going to be another enzyme. And that enzyme is called, let me find it, DNA ligase. And so basically what DNA ligase is going to do is it's going to go after that, and it's going to clean up all these messy junctions here, and it's going to put DNA straight across it. And so basically, that's a lot of stuff going on. What is all of that doing? It's making sure that that message that was found in the DNA is copied to that 2 new strands of DNA on either side. And there's some videos out on YouTube about how DNA replication works, and they put together some computer animations of it, and it's wild. It doesn't look like this at all. You have the lagging strand coming back upon itself. So it's pretty amazing. Or you could even read the story of Okazaki, the person who came up with this idea of how these Okazaki fragments work. Another fascinating story, but we got to finish. And so basically, what I want to talk about is origins of replication, or where DNA replication starts. Well, in life, there are basically 2 life types. We've got the prokaryotics, which is going to be the bacteria and the archaea, and then the eukaryotics, and that's going to be like you. And if you're prokaryotic, you're going to have a single loop of DNA. This is actually a plasmid, but it looks the same way. You have a strand of DNA in a perfect loop. And so for them, they can just simply start copying it on this side. The origin of replication is at one point. They move around, and eventually what they'll have is 2 strands of DNA. It's going to be an exact copy of that. And again, in binary fission, those become different cells. But in us, we have such a long DNA that we have to wad it up to even get it to fit in a chromosome like these pictured right here. In other words, your DNA in a cell is going to be like that long. And so if we were to start on one side and start copying it, it would take forever. And so basically what happens is we work in 2 directions. So basically there will be a site of replication where it starts here, but we're going to have it moving in this direction and moving in that direction. And so basically that diagram that I just showed you, I think this would be a better picture of it. That diagram where we had the DNA here, and then we had those new strands of DNA that are being formed. This would be one of those replication forks, we call it, but there'd be another replication fork at the other side. And also in eukaryotic cells, we'll have multiple sites of, or multiple origins of replication. So we'll have one here, we'll have one here, we'll have one here. In other words, when we're copying the DNA, it's going to start copying in a bunch of different points, and then those replication forks will move towards each other until we eventually have two strands of DNA.
Oh.
And so again, DNA replication, super important. It's incredibly accurate. It rarely makes mistakes. And I hope that was helpful.
Thanks.
Made up of millions of cells.
White.
Human beings are made up of millions of cells. Inside every cell lies a nucleus which holds 46 chromosomes. Our chromosomes carry genes which make us into human beings. Our chromosomes carry genes which make us into human beings. Our chromosomes are numbered from chromosome 1 to 22, with chromosome 1 being the largest chromosome, and chromosome 22 being the smallest. The last pair of chromosomes are the sex chromosomes, with boys having an X and a Y, and girls having two X chromosomes. A Robertsonian translocation carrier describes a situation where someone has 45 chromosomes instead of 46. Robertsonian translocation only occur between the acrocentric chromosomes.
Oh, okay.
These are chromosomes 13, 14, 15, 21, and 22. What happens is that two acrocentric chromosomes get stuck together, making one large chromosome. The commonest chromosomes to become stuck together are chromosomes 13 and 14, and the next most common are chromosomes 14 and 21. Other possible translocations occur much less frequently. A Robertsonian translocation carrier is healthy. However, problems can arise should the Robertsonian carrier wish to have children. To become a parent, you have to make a mature egg or sperm. Each parent only hands on half their chromosomes into the egg or sperm. Normally, each pair of chromosomes come together, exchange genetic material, known as crossing over, prior to dividing. For Robertsonian translocation carriers, this process is more complicated. In this example, Carl is a translocation carrier. He has one chromosome 13 stuck to chromosome 14. He also has another normal standalone chromosome 13 and 14. If he hands on the normal chromosome 13 and the normal chromosome 14, then the child will be healthy and have normal chromosomes. If he hands on the translocated chromosome on its own, that is the 13 and 14 stuck together, his child will be a healthy translocation carrier like himself. However, if Carl hands on the translocated chromosome together with one of the standalone chromosomes 13 or 14, the baby would have a whole extra chromosome 13 or 14, as Carl's partner will hand on a standalone chromosome 13 and 14 too. The baby will end up with 3 copies of either 13 or 14. This is known as trisomy chromosome 13 or 14. Babies with trisomy 14 will miscarry. Babies with trisomy 13, known as Patau syndrome, miscarry, although some may survive to birth. The condition is not compatible with life. If Carl carried a translocation involving chromosome 14 and 21, he would have a risk of trisomy 14 or trisomy 21, known as Down syndrome. The risk of having a baby with Down syndrome is higher if the woman, example Carl's sister, carries the translocation. Translocation families can also have a history of infertility. There are other very rare disorders which can occur with specific translocations. Your local genetic team would explain what your translocation means for you and what your specific risks are.
Wow.
Welcome to biology.
Hello. Hello. All right, let's take a break. I kind of want to sleep for an hour, to be honest. I want to sleep for an hour. No. Maybe if I sleep, then I won't be able to. Well, then it's gonna. Then it might mess up my sleeping schedule. No. Actually, maybe it's better we just continue it like this. Let's just continue. I mean, let me take a break, but no sleeping. No sleeping. Okay. I've been awk. Hopefully, when I come back, I have my energy. Okay.
What's going on?
Dude, I've been muted all that. I said I need to get my retainers. And also, I think we work out a little bit while we watch the lady. Because I need some energy. I need some energy. I need some energy. Do-do-do-do-do. All right. Let's get pumped up talking about some biology. I don't want to go too much. Stop. Why have you done this? Huh? Any issues before? There you go. Let's peel that side. There we go. Try now. Oh, too much. That's okay if I go a little further back, like here. So maybe we'll switch it. All right, let's go.
Today's lesson is about alternative splicing. Now, first let's talk about what just regular splicing is. Splicing is a post-transcriptional process in which introns are removed and exons are joined together. What does this mean? This means that in a pre-mRNA transcript that's made in the process of transcription in a eukaryotic cell, there are introns, which are non-coding regions, exons, which are coding regions. The introns get spliced out. This can confuse students because in versus out, but in stands for intervening sequence, X and the exon stands for expressed sequence. So it's the exons that are joined together into the mature transcript. Now, alternative splicing is a regulated process where there are multiple protein isoforms that can come from the same pre-mRNA transcript. So these multiple protein isoforms are encoded by a single gene via exons, parts or exons or introns being differentially joined or skipped. Now let's look at a picture of this. Right here, we have an mRNA transcript. It needs to be spliced. The exons are the parts that have different colored patterns, so and the white portions are the introns. So the introns get spliced out. Some of them are degraded. Some of them have regulatory processes, which we'll touch on in just a minute. But the exons, you see there's 4 exons here, and in this example, they can be differentially joined or skipped. Differential, this is one of the reasons why a synonym of alternative splicing is differential splicing, but they can be joined or skipped in different ways. So for example, in this isoform, we have this exon, and this exon, but this one has been skipped. In this isoform, we have this exon, and this exon, but this one has been skipped. So in alternative splicing, you have situations where multiple protein isoforms, like 2 shown here, and often even more than 2, can be encoded by a single gene. And this occurs because exons, or even different parts of exons, or introns can be joined or skipped in different ways, resulting in a lot of different combinations. So this isoform and this isoform, remember that these are still mRNA transcripts. They have not been translated into protein yet, but they do code for different proteins now, because this mRNA transcript and this mRNA transcript have different sequences. The fact that they have different sequences means that once they are translated at the ribosome into protein, those proteins have different structures. Now, the structures can be related. For example, they both have this component here. They both have this component here, although in this one they're separated, in this one they're together. This one has a different component at the front. So they've got different structures, related structures, but certainly with differences. And these different structures can lead to different functions.
Makes sense.
And so you can have these different protein isoforms that are all from the same gene, but because of alternative splicing, they can carry out different functions in the cell. Now, I also want to take a minute to talk about the fact that in humans, as many as 95% of multi-exonic genes, that means genes that have more than one exon in the transcript, so 95% of multi-exonic genes are alternatively spliced. So this process is a very, very common one in most eukaryotes, including humans. And the really great thing about alternative splicing is that it very, very much increases the diversity of proteins encoded by the genome. Because you can get proteins that, while they might have related structures, they have different functions, all coming from the same gene. And this is why when the human genome was first sequenced by the Human Genome Project, scientists were very, very surprised, shocked to find that such a small portion of the human genome actually codes for proteins. And so much of the rest of the genome is regulatory DNA. Some people will call it junk DNA, but we know now that that's not really true. And people thought, well, if such a small portion of the human genome codes for proteins, how do we get so many proteins? And then we learned about alternative splicing, and suddenly it all made sense. Let's talk just very briefly about the mechanism of alternative splicing. It is highly, highly regulated. It's not something that just sort of goes off randomly. It is regulated in part by sequences within the mRNA transcript. I said earlier that when these introns get spliced out, sometimes they're degraded, but other times the introns themselves, which are just a sequence of nucleotides, can be highly regulatory. They can inform other components acting in this mechanism on how to act, where to cut, where to join. Also, there are various proteins that play a role, specifically two types of proteins. The first are activator proteins. The second are repressor proteins. And these do what you might think. The activator proteins activate certain aspects. The repressor proteins repress certain aspects, and this controls which places get cut, which places get skipped, which places get joined. And also a major component of this process is a large complex of RNA and protein that work together. This complex is called the spliceosome. And the spliceosome works along with the activator proteins which activate it, repressor proteins which repress it, to go and cut in the right places and join in the right places to get these different transcripts that eventually lead to the different protein isoforms. So that is it for this video on alternative splicing. If you're interested in learning about post-transcriptional modifications like regular splicing, also 5' capping, the 3' poly A tail, please see my video on the post-transcriptional modification of mRNA.
Thank you.
.com/MCAT. And in this video, we're going to look at zwitterions and finding the charge of an amino acid. Amino acids are often drawn in the neutral form, such as glycine represented here. We have the alpha carbon with the hydrogen and side chain, the alpha carboxy group, and the alpha amine. That's how we get amino acid, an amine and an acid. But the problem is that with the amine being basic and the carboxylic acid being acidic, This is not the correct form for drawing an amino acid since acids and bases will react with each other. If I put these two molecules together, nitrogen would use its lone pair of basic electrons to grab the acidic hydrogen from the carboxy group, giving it back the electrons. And when enough amino acids react with each other, we would get something that looks like this. The carboxy group is now deprotonated to give us a negative carboxylate. The amine group now has 3 hydrogens because it's protonated, no longer has a lone pair, but gets a positive charge. Which is the correct form in nature? Depending on the pH, you're more likely to see this form in nature. The neutral form cannot exist because of the acid-base interactions. In nature, they're not going to react with each other. They're going to react with a solution, but the idea is the same. We're going to get a Zwitterion or dipolar ion. Zwitterion comes from the German word Zwitter, which means double and ion charged. The Zwitterion has at least 2 charged groups on the molecule. Acidic and basic side chains can have a 3rd charge in their variable group. Let's break this down and see how you find the charge of an amino acid at any given pH. The key here is to recognize that acids will donate a proton and bases will accept or attack a proton. If you're not solid with this concept, make sure you
If H plus is too high, H plus is too high. If the pH is too high, the proton will say goodbye. If the pH is too high, the proton will say goodbye. The pH is too high, the proton will say goodbye. The pH is low. The pH is low. What was it if the pH is low? pH is low. If the pH is low. I think it was if the pH is low. Proton doesn't want to leave. Let's take a look at what it was. pH is high. Finish this video. I'll stop working out. We'll go kind of clean up a little bit. We'll start Anki. We have, I think I might go till Anki. I think realistically speaking is going to take maybe 2 hours. So then we'll study for another 2. At least try to see if we can do either 1 or 2. I'd be happy if I get to 2 lessons today though. And then I got to add them, and then I have to read the high yield. If it's only 2, then that's what I'll do. If the pH is high, proton says goodbye. And goodbye. Fewer protons. Deprotonated. What about the other one? I got slow internet, sorry guys. If the pH is high, proton will say goodbye. If the pH is low, proton will stay. Right? Oh, if the pH is low, proton sticks and stays. Proton low sticks and stays. Yeah, sticks and stays. Sticks and stays.
To review the acid-base tutorial linked below. Once again, we have the neutral form of glycine. In order to figure out the charge, you want to start with a neutral form and then look for the pKa values. The pKa values, one for each acid or base, is going to tell you at which pH it's going to gain or lose a proton. To find the charge, ask yourself, what is the pH of any ionizable group, and will that group be protonated or deprotonated based on the pKa?
Let's see, I remember carbonyl is going to be, oh man, I think carbonyl is going to be 3, and then amino group is going to be 8, and then aspartate, include a mate, it's going to be 4, histidine is going to be 6, also nitrophysiological pH, and then you have and then I think we have L and E. And then we have LA, which is lysine and arginine. And then lysine is going to be 11, and arginine is going to be 12.
Before we look at finding amino acid charge at a specific pH, we have to understand the relationship of pH and pKa. The acid-base tutorial series linked below explains the relationship of Ka to acid concentration. Ka is equal to H plus times A minus over HA, and that tells us that Ka is proportional to the H plus concentration, where H plus concentration tells us the pH. From Ka, we can find the pKa, given that pKa is equal to negative log of the Ka. And finally, the relationship of pH and pKa can be found with the Henderson-Hasselbalch equation, where pH is equal to pKa plus the log of conjugate base over acid. If you're not comfortable with this, see the tutorial link below. So what do we make of this expression? pKa tells us how likely the molecule is to take a proton from solution or donate a proton to the solution. And what does the pH tell us? Well, if we have a low pH, that means we have an acidic solution. An acidic solution means that we have lots of H plus floating around, so many H pluses that we just start pumping them onto the molecules dissolved in solution. A high pH tells us that we have a basic solution. Basic solutions have lots of OH minus. And OH minus as a negative ion is looking to take protons away from our molecule dissolved in solution. Now you have to compare the two. How does the acidity or basicity of the solution compare to the molecule's desire to hold on to that H plus? When you're comparing the pH and the pKa, just think of it as a battle for the proton. The higher value has a stronger desire for the proton and takes it away from the other. If the pH is higher, the solution wins, and if the pKa is higher, the molecule wins. When the pH is less than the pKa, we're looking at a low, just think of it as a battle for the proton. The higher value has a stronger desire for the proton and takes it away from the other. If the pH is higher, the solution wins, and if the pKa is higher, the molecule wins. When the pH is less than the pKa, we're looking at a low pH and therefore an acidic solution. Which one wins? If the pKa is higher, the molecule is stronger and the molecule takes the proton away from solution. You can also think of it as a low pH has a lot of protons and therefore some of it gets donated to the molecule. Therefore, if the pH is less than the pKa, the molecule will be protonated. If the pH is greater than the pKa, we're looking at a higher pH or basic solution. The pH means that the solution wins and takes the proton away from the molecule. That means the molecule is going to be deprotonated. And finally, when the pH is near the pKa, we have a stalemate. The pH representing the solution wants the proton just as strongly as the pKa, which represents the molecule, and this puts us into the buffer zone. If the pH is equal to the pKa, then we have a 50-50, meaning half the molecules are protonated and half are deprotonated. But if the pH is within 1 unit of the pKa, you're still going to see the buffer zone, but you'll have more protonated or more deprotonated depending on the direction. When the pH is within 1 unit of the pKa, but the pH is lower, you're going to have more protonated than deprotonated. If it's higher, you'll have more deprotonated than protonated, but still within that partially charged region. Amino acids have a carboxylic acid in their backbone. So let's look at acetic acid, a very simple carboxylic acid with a pKa of approximately 4.8. What does this tell us about the molecule? Acetic acid is happy to donate its proton depending on the solution. If acetic acid is dissolved in an acidic solution, we have too many protons, and that means the Le Chatelier's principle says we push the reaction towards the reactants to the left, and we protonate acetic acid. If acetic acid is dissolved in a basic solution, the base, the OH-, is pulling the protons out of equilibrium, and that means Le Chatelier's principle pushes the reaction to the right, favoring products, and we deprotonate the acid. Let's look at different pH ranges. We'll start with a pH that is less than the pKa. For example, if pH is equal to 2. A pH of 2 is significantly lower than 4.8, and that means we have so many protons in solution that we're going to protate every available acetate and get acetic acid. The charge is equal to 0. We have a neutral.
pH is lower than the pKa. pH is low. Proton will stay glue.
Molecule. If the pH is equal to 4.8, pH is equal to the pKa, we're going to get 50% protonated and 50% deprotonated. Half the molecules grab a proton, but the solution takes the proton away from the other half of the molecules. The charge in this case, the average charge of all the molecules in solution will be equal to -1/2. Why -1/2? We have a charge of 0 for the protonated form, a charge of -1 for the deprotonated form, and the average between 0 and -1 is -1/2. This is an estimate. At pH is equal to 4.8, it's -1/2. As the pH goes up, the charge becomes more negative. As the pH goes down, the charge becomes less negative, with the ideal buffer range within a pH unit above or below the pKa value. If the pH is equal to 3.8, we have a 10-to-1 ratio of protonated to deprotonated following the Henderson-Hasselbalch calculation. If we raise the pH all the way to 8, it's a very basic solution. We have an overwhelming amount of OH-.
Yeah, Mom? All right, thank you, Mom. Ooh, look what we got. Look what we got. We got some corn. Basically, it's like corn oatmeal, I guess. Corn oatmeal. All right, let's continue.
And the OH- is much more desperate for the proton than the acetic acid. That means OH- will take away all the protons, and we have acetate in solution for a charge of -1. The numbers will change slightly on an amino acid because the pKa of the carboxy side chain will vary depending on what else we have nearby, but we're going to use the same principle with a specific pKa value. Amino acids have amines on their backbone, so let's look at an alkylamine, in this case methylamine.
So, more bread.
But since we're looking at a pKa and methylamine is a base, we have to look at the conjugate acid protonated form methylammonium. Methylammonium will be in equilibrium with its conjugate base methylamine, giving off a proton in solution. Methylammonium has a pKa of 10.6, which tells us a pH of 10.6 will give me a buffer between methylamine and methylammonium. If instead we try to apply a pKa value to a base, we're calling this base an acid, and methylamine can actually act as an acid or a base. Well, the acidic form of this molecule is going to give us CH3NH with 2 lone pairs and a negative charge on nitrogen. This is a very, very, very strong conjugate base, and you're not going to see this in the side chain of amino acids. Amino acid nitrogens will accept a proton to get a positive charge or donate a proton to become neutral, but the neutral amine will never donate a proton to become negative in physiological conditions. Let's see what happens at different pH values. If we start with a pH significantly lower than the pKa, let's put the pH equal to 7. This means, compared to the methylammonium's desire to hold on to that proton, the pH is much, much, much more acidic. That means the pH has so many protons, it doesn't want the proton from methylammonium. The pH is lower than the pKa, and so the molecule wins. The form is going to be methylammonium, CH3NH3+, and the charge is equal to +1. If we raise the pH well past the pKa to a value of 13, the pH is higher than the pKa. That means the pH, the solution, has a stronger desire for that proton. Methylammonium will give up its proton to give me the form CH3NH2 because we took away the third hydrogen, and the charge in this case is neutral. It's not negative because we started positive, so we dropped down to neutral. Acetic acid started neutral, so we drop down to negative. And finally, if we take a pH that is approximately the pKa value, for example, a pH of 10, it's slightly less than the pKa. That means it's slightly more acidic than the pKa, but we're still in the buffer zone. Because the pH is within 1 pH unit of the pKa, but it's towards the acidic side, we're going to get the acidic CH3NH3 plus in a higher concentration than the CH3NH2. And that means the charge will be somewhere between 0 and +1. And so we can say that 0 is less than the charge, which is less than +1. The exact number can be calculated using the Henderson-Hasselbalch equation, but on the MCAT, you don't have a calculator, so you're not expected to know the specifics. Instead, you have to be able to pinpoint the range. If the 50-50 range will be +1/2, and it's more acidic, that means we're closer to the +1, it'll actually be somewhere between +0.5 and +1. Let's apply this to the amino acid glycine. The pKa for the carboxy group is 2.3, and the pKa for the amine is 9.6. Let's see what happens when we have the pH less than, greater than, and equal to every pKa value. Let's start at a pH is equal to 1. pH 1 is less than both pKa values. That means the solution has more protons, and the solution will give protons to the molecule. Or think of it as the pKa is higher than the pH, and so the pKa's desire for the protons win. The amine group is protonated to NH3+. The carboxy group is The amine group is protonated to NH3+. Okay. The carboxy group is protonated to OH. And if we add up both charges, we get +1 for the amine, 0 for the carboxy, for a net Q of +1, where Q is the charge.
Okay.
If we raise the pH to the first pKa value, we're going to get a buffer at the first pKa. The carboxy group will be partially protonated and partially deprotonated, which means half of the molecules will have a -1 charge, half of the molecules will be neutral, so we'll say that the charge is equal to -1/2. The amine has a pKa greater than the pH and will be protonated for a charge of +1. The net charge of +1 minus 1/2 is equal to +1/2. If we raise the pH somewhere between the two pKa values, for example, pH is equal to 7, that's very near physiological pH, that's where we expect to see the zwitterion, but let's prove it. The amine pKa is higher than the pH, and so it'll be protonated, gives me a charge of +1. The carboxy pKa is lower than the pH, so it'll be deprotonated for a charge of -1. If we add a +1 minus 1, charge is equal to 0. This is our zwitterion. I want you to pay attention to a trend that's happening here. As we raise the pH, we went from +1 and we're dropping to +1/2, +0, so we kept dropping half. I want you to realize with me that if we raise the pH to the next pKa value, for this amino acid, it should be -1/2, and if we raise it above the pKa value, it should be -1. Let's prove it. We'll bring the pH to 9.6, which is the pKa of the amine. That means half the amines will be protonated, half will be deprotonated. Protonated amines have a charge of +1. Deprotonated amines are neutral, giving me a charge of +1/2. The pH is much greater than the pKa, and so the carboxy group is deprotonated for a charge of -1. +1/2 minus 1 is equal to -1/2 as we predicted. And finally, when we bring the pH well above both pKa values, we
You like the other video better. Let's watch this guy.
About the gel electrophoresis and different types of electrophoresis techniques for a while. And this is going to be another video about native gel electrophoresis. Now, what is native gel electrophoresis? Or you may also heard the name of native, PAGE, or native phase. Phase means polyacrylamide gel electrophoresis. It's a type of electrophoresis that we have already discussed. The native page is another small verification, small varying part of the page. So what is a native gel electrophoresis? Native means native is its original form, right, of something. In this case, the native means original form of the protein. Because when you talk about native gel electrophoresis, we are definitely talking about the electrophoresis of protein samples, not DNA samples. And the electrophoresis of protein is conducted with polyacrylamide gel, right? Because in that case, we simply call it SDS, polyacrylamide gel electrophoresis. So these are the two different terms, SDS page and native page. So SDS page, in case of SDS page, we've seen certain things. In case of SDS page, we've seen that the protein, whatever protein we take, let's say proteins are in 3D conformation, right? It is having different kind of intra-protein, different linkages.
All right, let me just wash my hands real quick. Let's relax a little bit. I feel like I have energy now. So I think we're good. And a good workout. Somewhat decent. So we got the energy, we got the food. Let's clean up and study some more. Over the desk, just the camera. What happened? Oh, hey, Jack. Jack is back. I don't know what you guys can see. I think I might need to zoom in a little bit. Is that better? I think so. Hey, Jack. Welcome back. Also, you're studying with very stress for living. You know, you're probably fine. Yeah, I was tired earlier. I'm feeling okay now. I feel like I got a little bit of energy back. I think, yeah, I'm still pretty tired. I'll take a shower tonight. Warm shower and feeling tired should help me fall asleep quicker now. At least that's the idea.
Amino acid bonds present there. But we treat it with SDS, sodium dodecyl sulfate. Now, the sodium dodecyl sulfate is a kind of detergent which is tagged with this protein, and it is having two different purposes. One is that it breaks down the different bonds that are present between those amino acids, the intra-protein interaction, the different motifs, and all those tertiary structures are broken down into smaller fragments. And what we get is simply as a primary structure of protein. Simply amino acids are attached with each other all together. That's what the structure, the linear structure should be produced prior to the SDS stage. And that's the job of SDS. And also it will tag the protein with negative charge throughout the body so that it can migrate to the electric field towards the positive electrode. That is the purpose of SDS, adding SDS in SDS page. But in native page electrophoresis, we use the electrophoresis process to separate the protein as it is. I mean, we do not allow the protein to be degraded or make them linearized. They are present, whatever 3D structure they are in, and they are separated based on their, normally based on their size, shape, and charge. But remember, if you look at the SDS page, normally the proteins are separated based on their size, that is based on their molecular weight. But in case of native page native electrophoresis, we can separate protein based on their shape, size, and charge. So if you look at here, it is a type of page used to separate protein based on the charge, mass, and shape that we have already seen. Now, this is helpful in detecting different things like amino acid content. That means the different properties of amino acids, or properties, different type of amino acids, whether the protein is consisting of more hydrophobic or hydrophilic amino acid or not. Then protein-protein interaction study is possible by native gel electrophoresis. Protein nucleotide, I mean, is there any region of nucleotide or DNA that the protein can bind? So there are different domains inside the protein where the protein is having a particular unique structure with which it will bind with DNA or RNA. So if there is any structure like that, we can have an idea about the structures by using this native gel electrophoresis. Or we can also see different kind of structures like molten globule structure and different motif structures of proteins by using native gel electrophoresis. And why? Remember, normally in case of SDS, we break them down and the SDS is added so that we get linearized segments of those proteins. And then we add and load them in polyacrylamide gel, and we know they're separated based on their molecular weight. So the smaller will travel the farthest here, and then the large and large, so on, it will go on like this. But if you remember, in case of native gel electrophoresis, the idea here is that normally the proteins are present. Let's say this is a protein which is folded properly. And this protein is having its own charge. Whatever folding conformation the protein has its own charge present. It can be slightly negative or highly negative, slight positive or hugely positive. It can be many different types. So it has a kind of its own charge. And as it is, this charge of protein depends on the amino acid sequence that are making this protein, right? So the different types of amino acid sequence, the presence of the type of amino acid sequence denotes what kind of charge this protein will have. So once that thing is there, I mean, this is one thing to think about. And another thing is that as we are not breaking this structure down, so the thing is, in the electric field, let's say this is the electric field, we apply this electric field to particular, let's say this, and we have loaded these proteins out there. So let's say this is a protein which is loaded out there, two different proteins. So this is the blue one, and we also loaded a green one. So we have the proteins loaded here. And as they migrate towards a particular direction, now the movement of these proteins in this electric field will depend on the net charge of the protein itself, because we are not tagging any charge to this protein on themselves, right? So it is completely based on their own charge that they have. And the charge of protein is depending upon the type of amino acid sequence are making the protein, right? That's a very important point here. So they are migrating this through this electric field depending upon their size. And if now let's say this whole movement of this protein is influenced, as it is also made up with polyacrylamide, this is influenced by the shape also and molecular weight also, because as they have a three-dimensional conformation, So a protein can have a different kind of shape, and different kind of shape of the protein allows the protein to pass through the polyacrylamide polymer pore at different rate. So if we apply the same electric field throughout the time, right? Or let's say most of the cases what we do is slide electric field, or kind of we keep this neutral zone. We keep a neutral electric field throughout this place. It's all about the protein's own charge and the protein's own shape. Obviously, protein's own molecular weight, which takes the protein move from one direction to another and be at different positions. So what we can guess from that is that from mixture of proteins, by looking at the position of the protein during this type of separation, we can tell a specific type of structure of protein, a specific type of structure like molten globule structure. So we know that if this is a molten globule structure of protein, if we have the molten globule structure of the protein, and if we run it with native phage, it will be landing somewhere here at this gel, because if every time we do the experiment, it lands kind of similarly at the same area. If we maintain the phage concentration, I mean the polyacrylamide concentration at a level. That's the thing. We allow the protein to pass and migrate on their own to get more information about the protein structure, more information about the protein size and shape, right? That's why we use native gel electrophoresis instead of SDS phage. Because in SDS phage, we want those proteins to be separated from each other. So majorly in SDS phage, we use them to actually separate them, we actually to get the different molecular weight proteins out there. But in native gel, we want to see how those proteins are behaving in the electric field. So what is the charge mass behavior of that protein in the electric field? And another important thing about this native gel electrophoresis, as those proteins are not degraded, so after this migration is done, we don't even know not to use any kind of protein tagging stain. We can use any enzymatic stain or enzymatic reaction or coloration to know the presence of the protein bands or presence of proteins, because the proteins are active at this particular point. And even we can take cut this different phage gel open and take out the protein, and we can extract that protein, and that can be functional during this particular area. So if you see here, this is the condition we have. Normally we can run it a vertical, or we can run it the horizontal gel electrophoresis. So we load the buffer, then we load the protein sample, then we start the power supply, then we after some time we take out, once the process is done, we take out the gel, we stain it, and we see the position of proteins. This is the process. But remember, in this case of native versus SDS, I've already discussed, is that in SDS it is single, so you can see straight, very resolved bands and different locations. But we don't want that in case of conventional native phage. What we want is how that protein actually behaves. That's what the primary thing for us to determine using the SDS and using the native phage or native electrophoresis. So that's kind of it about the native electrophoresis, and I hope this video is helping you. If you like,
sure, thank you.
Layer here, we have a net charge of 0. In the last video, we looked specifically at the charge for glycine at a pH of 1, 7, and 13. At a pH of 1, we got a net charge of +1. pH of 7.
Yeah, this is the video, but let's go through another time. I'm tired of watching YouTube videos for now, to be honest. Let's go ahead and fix this. I like this overview. That's for later. Oh, that's I need to finish. I like the overview here. This one should be here. And I think that's it. Oh, let's Anki. Almost forgot to do Anki. Oops. This one. Woo! All right, let's get started. Let's write it from the top down, I guess. What other way do we got? Okay, endergonic reactions will require energy. Positive delta G. initiation, elongation, termination. Positive charge. Net charge is 0. That's electric current.
The protein value for.
I can watch you tomorrow. I'm not going to do it right now. Too much time. Multiple because of one. DSI. DNA. Chromosome. Termination. Cell embodying. Catalyzes interconversion, the interconversion of isomers. Prokaryotic ribosomes are, so I think eukaryotic are 70, prokaryotic are 50. No, prokaryotics are 60, 70 and 60. Ah, I messed up. It was 78. No. Excuse me. Enzymes do not alter the delta G or delta H. The Gibbs free energy or enthalpy in the final equilibrium position. And the free energy gives free energy. Northern blotting.
Previously, we discussed
Everything just points back to Andrew K. methionine, met, M, hydrophobic, nonpolar. LD indicates relative, and SNR indicates absolute. RNA uses a ribose sugar and uses a uracil instead of thymine. Heterotropic. What did the guy say? It doesn't affect shape, it affects what?
So for the differences between one of those things, hemoglobin trophic with the subsign 2 is, in fact, changes Km value. Is it
Affects the Km value. Affects the Km value. Okay. I'm not sure. Singer. Oh, singer. And then it can be flipped, right? Or something like that? Okay. One half of a chromosome? No, chromosome. Mismatch. No, this is timing timers. Nucleotide excision repair. Yeah. Phenylalanine is regular amino acid group. You have the amine group, the carboxyl group, and then for the R group, we're going to have a benzyl ring. Not a benzyl, a phenylalanine. Benzyl. Not a benzyl. I don't think it was even a benzyl. It was just a phenyl group. It's so slow. That's okay. My internet is slow, and that's okay. Yeah, just a phenyl group. Just a phenyl group. Regular old phenyl group. Regular old phenyl group. Phenylalanine absorbs UV light. Hydrophobic. Yep. Okay. That's okay. PCR. bake it, cool it down, and then just leave it room temperature. Rinse and repeat. Primary, post transcription or modification. The y-intercept is 1 over v max, slope is km over v max, and then the x-intercept is negative 1 over km. We have genes that are regulated together. Operons, like operons, like operons. Operons, yeah. Operon, operon. Yeah. Yeah, the three systems come used under separate charge. All those DNA RNA importance according to their size and charge. PCR relies on a thermostable DNA polymerase called what? Oh, called. I'm not sure. I don't remember. I can't think of it anymore now. Tac polymerase. Tac poly. Yeah, it came from that one, whatever, archaea organism, I think, or something. Okay. Oh, that's KM. Reason. Acrocentric. Histidine has H. Polar basic, hydrophilic. Histidine has the amidazole group, and neutral at physiological pH. Amidazole. Isoelectric points. Excuse me. Oh, right, temperature. Well, first we're gonna make it, so I'm gonna go with like 98. Then we're gonna cool down, so I'm gonna go like 52, and then we're going to just kind of leave it a room. Oh, is it room temp? Well, I think we're just gonna let it cool off. So we're gonna come up. So we're gonna go a degree Celsius. Let's see. And 96, 55 to 65, and then 72. Denaturation, annealing, and extension. Okay. These are relies on a thermostable DNA polymerase called Taq polymerase. We're going to heat. We're going to find our target gene. We're going to heat. Post-crucial DNA to the DNA. We're going to cool down, add the primers, anneal to the complementary sites. Then we're going to heat up, and Taq poly will begin polymerase synthesis. And just repeat double our initial amount. Oh, did I do good? Oh, I should have redone that one. Whatever. Prokaryotic ribosomes are 70 Svedberg units, and then eukaryotes are 80. Let's go. Southern prokaryotes have one, eukaryotes have multiple. denaturation at around 98. Then we have reannealing at what is it, 55 to 65, and then we have extension at around 75. Oh, 72. RNA will be northern blotting. DNA methylation will decrease extracellular chromatin and will stop DNA binding proteins from interacting. Yeah. Silent mutation has no effect on protein synthesis because it's silent. These are enhancers, right? Topoisomerase. I believe it's attention to be in front of the helicase, right? Like in front of the helicase. Yeah. Oh, we got denaturation at I think it was denaturation at 95. Then we have reannealing at 45. Oh no, 45 to 65. And then we have extension at 72. Oh, it's 96. Do I really need to know? What did I say? 95? 95. In non-competitive inhibition, we have so in non-competitive inhibition, we have that the we have that it can go to the enzyme or to the enzyme substrate inhibitor or enzyme. Yeah, it's gonna be allosteric. It's gonna bind allosterically, and the substrate doesn't necessarily need to need to be bounded, I guess, bounded, but it will decrease Vmax, and since the substrate can still bind, it's going to stay the same. So Km will be no change. Vmax will go down, and we're gonna on the Lineberger plot we're gonna have both the graphs touching on the we're gonna have both the graphs touching on the x-intercept. And the y-intercepts, yeah. Slightly raised. Yeah. Conformational change of the enzyme substrate bound or not bound. Yeah, there you go. Yes. This is Sanger sequencing. Yeah, this is Sanger sequencing. And from here we can determine what our DNA sequence is, right? Chromatid, what happened? Weird way to say it, but okay. This is proline.
Proline, pro-P, hydrophobic, disrupts, is kinky, will cause kinks in the alpha helixes, and it will be assigned in beta term, making it really sharp turn with beta theta speeds. What are we? Repressors, suppressors. Oh, what? Transcription factors. Oops. This sounds pretty bad. Polymers of linear sequences of nucleotides. Wait. Nucleic acids? Yeah, I mean, polymers of nucleotides. With a sugar phosphate backbone. Add that in there. From the 3' to the 5', but synthesizes from the 5' to the 3'. Phenylalanine, you have your, amino group, carboxyl group, and then you add your phenyl, and it absorbs UV light. Phenyl group, phenyl. Yeah, phenyl group, phenyl. Absorbs UV light, though. I think that's pretty important to remember, huh? PCR. Non-competitive inhibition. The centromeres. I mean, it's kind of like a pentagonic cyclic structure that folds back onto itself and has a much bigger in the bottom left corner. Yeah, and it's kinky, causes kinks in alpha helixes on the beta turns. It's right here. It's nitrogen. Well, it just kind of folds back onto itself. Because this is the amino group, this is carboxyl group. Hydrophobic. The polymer, the primary structure called SDS. Right? Oh no. To cupto, I don't know, something. To cupto, I don't know. To cupto something? To mercaptoethanol. To mercaptoethanol. Sure. When there's no side chain, it's going to be pKa 1 plus pKa 2 divided by 2. Introns. Within the same molecule? Secondary. Post-translational modification. Sure, all these are examples. Phosphorylation, glycosylation, ubiquination, sumoylation, acetylation, lipidation, methylation, hydroxylation, disulfides. Capillaries. That central dogma. Polysystronic chain. Polysystronic chain. It's quite polysystronic chain. Did you know that? Asparagine. Asparagine M is a neat amide. It's short carbon train with two mides groups. No, with just an amide group, just one amide group. What did she write for N? Or this person? What did this person write for N? Oh, essential AA. What did I put again? Where's N, by the way? I don't see N anywhere here. This person not write N? It's asparagine. Asparagine is N. So where's asparagine? Oh. They didn't put it as N, they put A. That's so weird. What the heck? Why would you do that? Why would you learn it like that? Okay, well, whatever. But I think essential AA, do we really need to know that? Hello? Hello? Oh. I was so confused. I'm like, what is this? Private Tim Hall. Private Tim Hall. Sort of helicase. Oh, gotcha. Private Tim Hall. The day duration at 95 or 94 96. Renewing at 45 to 65, and then extension at 72 degrees Celsius. Yep. The tertiary. Mm-hmm. All right, we'll take a 10-minute. Is there anybody in the chat? Oh, I guess okay. That's right. I'll leave a message. Pin message. I don't know what to do. What you say? Yeah, no worries. Yeah. Today I'm more tired than usual. I'm more tired than normal. Way more tired than normal. But we did it. We're doing it. We got this maybe 20 minutes because we're breezing through transcription factors, and then polymers and nucleotides. And then, anyways, let's think here. And then we'll go there. Well, maybe. I don't know. This could be 30 minutes. I don't know. We'll see. But 30 minutes, and it's 9, and we got 2 hours, and then we'll just do. Honestly, we should still. Did I move her to? We should move last techniques here over as well. We can watch this tomorrow. Maybe we watch these math ones, to be honest. Or maybe we can wait. Yeah, maybe we can watch the math ones, I guess. Sure, why not? Might as well hit strategies too tomorrow, I guess, in the morning. We can duplicate that and just go to strategies. Yeah, we should watch that though. And what else on the playlist? I think that's about it. Did you say anything about Anki?
Learning the sciences for the MCAT's a drag. It feels like there's no way.
Do Anki faster? Why I hate Anki for the MCAT? Interesting. Let's duplicate the tab.
Learning the sciences for the
And let's go back to the playlist. I like the playlist, like the way it looks. It's really nice. Maybe we can watch some of the Yankee stuff tomorrow, see what they say. Ah. All right, let's go put some of the plates away.
Shoot. Should do it in the morning. Yeah, tomorrow morning I will. Process energy single chain coding for multiple proteins. In a single day, coding for multiple proteins. Multiple proteins. Coding for multiple proteins. I'm gonna go with alternative splicing. I'll take alternative splicing for 500, please. Why do my voice crack so much? I'll take 500. I'll take alternative splicing for 500, please. Thank you. Ding, 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 ding. Phenylalanine, phenylalanine, F. What? With wife. W tryptophan, Y tyrosine, phenylalanine absorbs UV light. That's all I want to get. That's all I want to get. Absorbs UV light aromatic. Of course, that's aromatic. Primary structure to mercaptoethanol. Secondary structure, tertiary structure, increase in accessibility. I'm going to say demethylation. Oh. Histone acetylation. Whoopsie daisy. In gel electrophoresis, small molecules move fast, large molecules move slow. It's the way of the world. Quaternary structure. Quaternary. Example: DNA and histone, chromatin connecting histone. Agarose gel has large portions to separate nucleic acids, and acrylamide has small pores to separate proteins. Polyacrylamide, not acrylamide. Polyacrylamide. I'll do that one again. It's suppressed, turn off. Suppressed. Repressed. Okay. 5' cap made up of a methylated guanine. Made up of multiple adenine nucleotides. Karyotic are 80 separate units. DNA is a bond made up of monomers called nucleic nucleotides. Nucleic acids? Nucleotides. Oh, I didn't know this one here. Yeah, it runs anti-parallel. Plasma. I want to say plasma. Wait. Nucleotides from two different sources. Nucleotides from two different sources. Created only in labs. DNA composed of nucleotides from two different sources. DNA composed of nucleotides from two different sources. What are you talking about? What are you talking about? I don't know. Oh, recombinant. A nucleotide. Ligase. Phosphate groups. Phosphate backbones. Exons. Promoter genes. Top of the box. Polyacrylamide. It uses non-denaturing conditions for the native. Chromatin. Histone core. Chromatin. Nucleosome. Nucleosomes into chromatin, into supercoiled DNA, into chromosomes. H1, H2A, H2B, H3. H2A, H3, and H4 maybe? Maybe. A nucleoside is a carbon sugar, let's say. Ribose carbon sugar? Nucleotide carbon sugar. Nucleotide carbon sugar plus a phosphate. Wait, what? I don't know. Phosphate carbon sugar. What? Plus a nitrogenous base and phosphate. Dude, whatever. I don't know. What are you trying to say here, bro? Okay. 5 carbon sugar plus the nitrogenous base and no phosphate. Oh, okay. And the amino acid is a Switter ion. Both a amino group and carboxyl group. Humans have 20 pairs, so total 46. Nucleotide is a nucleoside with 1 to 3 phosphate groups. Phosphate groups and allolactose. This extra DNA occurs in the cell cycle phase. This extra ferrous occurs in G2 using G's MSH2 and NOH1. Transition occurs in the cytosol, the ribosome. In the ribosome at the cytosol. Cytosol. The 5 carbon sugar plus a nitrogenous base and no phosphate groups is a nucleoside. Sweberg is a measure of sedimentation time. Yeah. Tendency of particles to settle out of fluid. It all depends on mass and shape. And they're not additive. DNA is a double helix and it runs anti-parallel. Italian DNA. Neighbor DNA? What does that mean? What the heck? Ha ha ha. Your histidine, his age, neutral physiological pH, pK of 6. Whoa, stop. No, you're none of those. You are tyrosine, you're aromatic, you're polar, You attack phosphate groups with this hydroxyl. Tyrosine TYR Y. You are yeah, aromatic. I mean, yeah, but I think you're polar, right? Yeah, polar. Was close. I was like messing up there. Uncharged. Excuse me, missense mutation. DNA. What are we talking about here? The nucleal, the pyrimidines. And 40S so attaches to the it attaches to the 60S ribosome, no? Oh no. Whoops, what am I talking about? What am I talking about? Attaches to the 5' cap. This is negative effector. Negative effector. Allosteric inhibition. Yeah. Oh, negative effector. Allosteric effector. Enzymatic activity goes down. Okay, you are non-competitive inhibition. Clinical is considered ambiguous and degenerate. Purines. Base nucleotide repair. Base excision repair. Base excision. Two conditions are met. We have the presence of lactose, and we have low glucose. Yeah, yes, produce a premature stop codon. Nonsense. You're speaking nonsense. You're speaking nonsense, man. Increases the accessibility of chromatin. So this is DNA binding proteins interact. This is histone acetylation. This is secondary. No, quaternary. Yeah, quaternary. Gel, large pores. This is agarose gel, and then polyacrylamide gel has smaller pores. Recombinant DNA. Monomers called nucleotides, nucleic acids, nucleotides. Long strands which run anti-parallel. Due to the phosphate backbone, with phosphate groups, or 1 to 3 phosphate groups. Nucleoside is a 5-carbon sugar plus a nitrogenous base and no phosphate groups. Watson Crick DNA is double helix runs anti-parallel. Pyrimidines, allosteric effector, change conformation, a negative effector, change conformation, reduces enzymatic activity. PRAs like adenine and guanine. What did the guy say? Searching for gold and silver. And this is we cut the pie. Sure. Non-deforming leading AP side. Base excision repair. Yeah. It's got one nucleotide. Attaches to the 5' cap. 5' cap. The final phase is the M phase, which includes meiosis, mitosis, and meiosis. Homologous chromosomes form. Homologous chromosomes form. Homologous chromosome form tetrads and undergo DNA recombination? No. I think so. Yeah. Recombination. Well, not DNA recombination, but recombination. DNA recombination. Recombination, but genetic diversity? What are we talking about here? Genetic. Oh, that's exactly kind of what I said. Even genomes can generate unambiguous. Germ cells? No. Gametes? Germ cells? Kinetics, within the movement, we're discussing kinetics, we're talking about the rate of a chemical reaction. Stated feeling antagonist and how quickly the mitosis leads to two identical daughter cells. Mitosis involves one division, resulting in two identical daughter cells. Involves two consecutive divisions, producing four genetically diverse. The population can churn out the ribosome, and then to immediately go into the Golgi apparatus. Oh, what? Whoops, I know. Oh, for both. Okay, never mind. RNA exits the nucleus and functions in the functions in the cytoplasm. Yeah. Recombination. Crossing over. I think it's the same thing now. Is crossing over the same thing as recombination? Not the same thing. So two different parts. I thought that's what it was. Maybe not really. Crossing over. Oh, crossing over to new combination process. That's okay. I know what it is. Mitosis involves one division resulting in two identical daughter cells. While mitosis maintains a chromosomal have. During meiosis, carriers of electrons and functional groups. The ribosome begins translating by matching codons from the mRNA. Codons. Codons to anticodons. Sometimes the polypeptide that is getting churned out the ribosome occurs in somatic molecules. Mitosis. It's almost identical to the coding strand or the sense strand, the non-template strand. A spontaneous reaction, reaction requires negative energy, often termed exothermic, exergonic. Sure, exergonic. I guess exergonic. Energy. Okay, exergonic. RNA is typically single-stranded. Those involve stages like PMAT, M stage. PMAT, yeah, PMAT. Prophase, metaphase, anaphase, telophase, and cytokinetic phase. Cytokinetic phase? The cytokinetic phase? Cytokinesis? Cytokinesis after PMAT? I'm pretty sure cytokinesis, I think. Here's a strand of an RNA called mRNA, messenger RNA. Pre-mRNA. The non-coding strand known as the antisense strand, template strand. Exonucleus. Mitosis. Okay, let's mention the equation. It's considered degenerate and ambiguous. Daughter cells and mitosas are two genetically identical daughter cells. The packaging chromatin is crucial for certain processes like DNA replication, DNA repair, gene regulation. While mitosis maintains the chromosome number of the original cell, mitosis by half, which is crucial for genetic diversity, propagating diversity in species. Species-specific chromosome number. Maintaining species-specific chromosome number. Maybe that again. Through meiosis. Meiosis undergoes integration to processes like meiosis 1 and meiosis 2. Oh, processes like crossing over, recombination, crossing over, and independent assortment. So one division resulting in there's some 4 genetically diverse haploids connects all together. Ligation. Enthalpy is often the bond equivalent to the energy stored in the bonds within a system. Meiosis is the process of formation of 2 genetically identical daughter cells. The 3 bonds. These bonds are formed between the third carbon on the right and the 5th carbon on the sugar. Third carbon will be the phosphate group. The 5th carbon will be also the other phosphate group. And the 1st carbon will be the nitrogenous base. Mitosis involves 1 division, whereas meiosis is integration through processes like crossing over and independent assortment. Crossing over occurs during meiosis with mitosis. mRNA is transcribed in the nucleus. This nucleus is with a small subunit which is made of RNA initiation. Proteins are commonly phosphorylated to upregulate or downregulate their function. Amino acids can be phosphorylated to include amino acids that can be phosphorylated include tyrosine, serine, and 309. A DNA can also be known as a phosphomimetic effect. Serine, 309, tyrosine, phosphomimetic effect. Good. The enzyme that reacts DNA, the enzyme that reads DNA is called RNA polymerase. If you're reading DNA in transcription, you're RNA polymerase. The reduction in chromosome number during meiosis is crucial for genetic diversity of sexual reproduction. Replication, DNA polymerase. Disulfides bonds, 2 cysteines. Wait, yeah, 2 cysteine residues. That's not gonna happen like that. A salt bridge in the context of proteins surrounding nutrient cultures is a combination of both.
ionic bonds and hydrogen bonds. Hydrogen bonds. Meiosis also introduces genetic variation. Evolution grows the number is crucial for sexual reproduction. Mitosis. Somatic body cells. Daughter cells and mitosis. Meiosis. Germ cells are producing gametes through meiosis. Okay. So this supply method that is getting turned out the ribosome is meant to go immediately into the RER. Crossing over. Mitosis also is a prophase. Remember my PMAT. Meiosis 1, meiosis 2. Meiosis. 46 chromosomes. mRNA shares in the nucleus as a small subunit of a ribosome, which is made up of RNA, ribosomal proteins. It's called the transcription bubble. Oh wait, what? I'm sorry, confusion. Reduction in chromosome number during meiosis. DNA polymerase binds the primer, adding DNA nucleotides from the 5' to 3' direction. The daughter cells and mitosis are genetically linked to the parent cell. In contrast, daughter cells and mitosis are genetically. The daughter cells and mitosis are genetically identical to the parent cell. Daughter cells and mitosis are genetically identical. Contrast meiosis, mitosis, home division, log functions. Ironically, complementary to both the mRNA strand and decoding strand. Nucleotides form hydrogen bonds. Reduction in chromosome number is crucial for sexual reproduction, ensuring genetic variation and keeping the same number of chromosomes and having less number of chromosomes, right? Having a constant chromosome count. Meiosis is a special form of division that produces gametes. Germ cells start out as diploid but produce haploid. Mitosis occurs in somatic cells, while meiosis germ cells start as diploid but produce haploid gametes. Mitosis. Prophase, metaphase, anaphase, telophase, cytokinesis. In meiosis 1, homologous chromosomes undergo recombination by the meiosis
The resulting cells have undergone degradation. "23 chromosomes. Oh, they have half the number already. They have half the number. Observe in kinetic, not thermodynamics, or equilibrium. Mitosis. Integration. So I keep getting them wrong. Due to crossing over. Crossing over independence from Mitosis reduces by half. Complementary DNA nucleotide. Complementary rRNA. RNA nucleotides. Maybe remember is CAC. If Q is greater than CAC, then we're going for products or reactants. And if Q is less than CAC, then we go from reactants to products. Daughter cells in mitosis are genetically identical to the parent. No, wait, daughter cells. Genetically similar. Yeah. Reduction in chromosome number their mass is crucial for ensuring a constant number of chromosomes from one generation to the next. Due to having 23 chromosomes. I don't know. Mitosis occurs in somatic cells to germ cells. What? 2 strands? Yeah, both strands. 2 strands. The chromosome begins with natural codons with anticodons. Daughter cells and mitosis are due to crossing over recombinant and recombination independent from it. Yeah. This leads to the formation of 2 identical daughter cells. Meiosis 1, meiosis 2, crossing over independent, which is crucial for keeping the same, having a constant number of chromosomes from one offspring to the next. Yeah, yes, that's something. Crossing over occurs during meiosis, but not mitosis. Meiosis, recombination and independence. Reduction in chromosome number of meiosis is crucial for genetic variant. Sexual reproduction. Mitosis occurs in somatic cells. Crucial for sexual reproduction. PMAT. Mitosis results in cells with. Mitosis results in cells with 46 chromosomes. The resulting replication fork. Meiosis. Mitosis occurs in body cells while germ cells. Meiosis. Resulting cells have 23 chromosomes, so 10, 1 N. and 1N. It's restricted to germ cells. Ensuring that the constant we have a constant number of chromosomes from one offspring to the next offspring. One generation to the next. One generation to the next. Due to multi-crossing over in independent assortment. The combination process of just generations process of crossing over in independent assortment. The reduction comes one number of dialysis is crucial for sexual reproduction. Let's go. Sheesh. R is 8.314 times joules over moles times Kelvin. Different from the ideal gas constant. Transcription, pre-mRNA to post-transcriptional modification. Keck, equilibrium constant. Gives you energy, describes the energy. Describes the energy change. Describes the energy change that's available to do work. That's left after that's just left overall, I guess. And also the energy that's released into the system. Available to do work. As uniform charge for the protein. Heterozygous. Dominance. Codominance. Incomplete dominance. Western protein, amount of proteins. There you go. Carboxylic acid backbone was 3. Amino group was 8. Aspartate and glutamate was 4. Yeah, that's what I said. Let's go. I still got it. Both alleles, 2 alleles are expressed in the phenotype. Codominance. Delta G prime is gives free energy monarch equation. It's determines spontaneity. Changing gives free energy, some point of interest in the reaction, understand the conditions. Okay. Ribosome begins transition matching codons with TR anticodons. Term wild type is mutation. Okay, it's the most common given no mutations. This looks like +/+. It's always AA homozygous dominant. Always assume it's homozygous dominant. Okay, T is temperature in Kelvin. That goes for propane. Goes for protein. Incomplete dominance. Negative delta G is gives free energy, and we have to assume it under standard conditions, 25 degrees Celsius, 1 atmospheric unit of pressure. I forgot the rest. 1 molar of all species. Gives free energy. Let's assume standard conditions, 25 degrees Celsius, 1 ATM, 1 molar for all species, including the products. Point of interest in reaction under some conditions. What do we see? 1 ATM, 1 molar of all species, the products. I think so. Dang, dude. Do Anki faster. Faster Anki. Oh, I hate Anki. Dude, I wanted to start this today. But if I'm putting it back behind by a week, then if I don't do 2 today, then that means that I can do 4 tomorrow and be caught up with this week. Maybe I'll do that because I want to rewatch. Like, I think, is this the video that I watched last time? This is the one I like. I don't really like the other one, but I might take some time to practice this because I don't want to not be able to do this on the actual exam. So I want to practice this, and then I'm practicing this. We'll watch the videos first and then practice using her. Well, I guess, okay, watch both those videos. Are they the same thing? Part 2. Watch your video, practice it. Glycolysis, we're like way out, but I have that, I don't know why. And then here's the stuff, that's just stuff we can think to do. And that might be it. I might just call it here, guys. I don't know, I'm just tired. I'm tired. I'm tired, but tomorrow let's do Anki first before anything. That way, it's more smooth. Let's do Anki first, then the videos to practice, and then the 4 videos, and then we'll read high yield and add those to the new cards. I think we should do 4 tomorrow. I think I'm gonna go here, guys. I'm sorry. Let's just get a fresh start, you know? Let's get a fresh start. Let's get a fresh start, please. I just want a fresh start. I just want a fresh start. Okay, so I'm just gonna call it here, guys. Thanks for watching. I appreciate you guys. All right, thank you. Bye-bye.